Okay, we can start, I think. Alexey Vladimirovich, you are ready?
Yes. Can you hear me? Hello?
Yep, we hear you.
Okay. So, should I start?
Yes, we're waiting.
Yes,
Okay.
please.
We not see your presentation.
Okay, I didn't share yet. So, should I start to share?
Yep.
Okay. Post disabled participant screen sharing. Hello?
A second. We have technical problem. Okay, can you try again?
Okay.
Okay, everything okay. We see your presentation. You can start.
Okay. Okay. So, hello everybody. Greetings from Fukushima, Japan. My name is Alexey Konoplev. Originally, I'm Russian environmental chemist. Back in 1977, I graduated chemistry department of Moscow State University. Today, I represent Institute of Environmental Radioactivity at Fukushima University, where I worked for last 10 years. Besides scientific research, I am giving 2 lecture courses at the university for graduate students. They titled Nuclear Disaster Studies and Environmental Radioactivity Sciences. So the title of my lecture today is Nuclear Disasters, Radioactive Contamination and its Effect on Humans and Environment. So let me briefly introduce you our institute, which was established in 2013, which clear objective to organize and carry out fundamental studies of the national and international level on behavior of Fukushima-derived radionuclides in the environment and their biological effects. The institute is located in the Fukushima University campus, 60 kilometers away from Fukushima Daiichi nuclear power plant. So here you can see the map of Japan. Here is Fukushima Daiichi nuclear power plant. And here is Fukushima city and Fukushima University campus, where our institute is located. So this is very convenient location to do a field research in contaminated area after the Fukushima Daiichi nuclear power plant accident. Here you can see the university campus, and here are 2 buildings belonging to our institute, and this small building is analytical laboratory where our equipment is located. And here is our team. It's not very large, but efficient. Okay, let me start from the start of the nuclear era. 16 July 1945, the first nuclear bomb test, Trinity, in New Mexico, US, was taken. So 2 atomic bombs were detonated over the Japanese cities of Hiroshima and Nagasaki in August 1945. So By the end of 1945, the bombing had killed an estimated 140,000 people in Hiroshima and further 74,000 in Nagasaki. In the years that followed, many of survivors would face leukemia, cancer, or other terrible side effects from the radiation. The use of two relatively small nuclear weapons in 1945 has resulted in increased levels of leukemia and cancers amongst atomic bomb survivors over a period of 70 years, with new illnesses and diseases expected for years to come. So let me briefly describe the long-term health effects of Hiroshima and Nagasaki bombing. The incidence of leukemia among survivors reached a peak of 4 to 5 times that of non-exposed control group in the years following the atomic bombing, before diminishing 10 to 15 years later. The health of non-exposed children of atomic bomb survivors has been intensively followed in recent years. These are children born to hibakusha, or bombing survivors, in the years following their parents' direct exposure. This second generation population includes some 200,000 persons who are currently approaching the cancer-prone age of 50, 60 years. In the radiation exposure damaged the genes of hibakusha, as it has done in animal studies, genetical transmission of radiation effects will be another long-term concern requiring years of treatment. A large-scale epidemiological study of this population is currently underway. So here you can see the subsequent nuclear weapon testing by so-called nuclear powers, which are, first of all, United States, then Soviet Union, France, UK, China, and recently India, Pakistan, North Korea. So, and on the graph, you can see a number of tests during the years, and you can see the blue is the US tests, red are USSR tests, and then, yeah, and pink is North Korea over here. Okay, and here you can see the explosion, so-called Baker shot of nuclear tests in Bikini Atoll in 1946. And here are the test sites distributed over the world. So, so most of Soviet tests have been made in Semipalatinsk and Novaya Zemlya. So the first test in the US was in New Mexico, and then in the islands of Pacific Ocean. So UK tested atomic bombs in Australia, and France in Pacific Ocean and Algeria. So here you can see the consequences, namely the annual global deposition of strontium-90 as a result of atmospheric weapons testing from 1958 to 1990. And you can see sharp increase of the strontium-90 deposition during the end of 50s and start of 60s. And then in 1963, there was international agreement taken which banned the atmospheric nuclear weapons tests. Therefore, as a result, there was a sharp decrease of the deposition of strontium-90, but not immediate. Why is it so? Because the radioactive particles after the nuclear bomb testing, they go up to the very high levels in the atmosphere, up to the stratosphere. And there they distributed over the globe and then slowly deposit on the surface. Therefore, the washing of this upper atmosphere took some time, but anyway, after several years, it diminished very seriously. Okay, let me say now a few words about the classification of nuclear accidents. So this classification is carried out in frame of International Nuclear and Radiological Event Scale, INES, which was introduced in 1990 by International Atomic Energy Agency in order to enable prompt communication of safety significant information in case of nuclear accidents. The scale is intended to be logarithmic, similar to the moment magnitude scale for earthquakes. There are 7 non-zero levels on the INES scale, 3 incident levels and 4 accident levels. There is also a level 0 when there is incident, but there is no serious consequences. The level on the scale is determined by the highest of 3 scores. First, off-site effects. Second, on-site effects and defense in depth degradation. So let's consider the level 7, which is called major accident. Major release of radioactive material with widespread health and environmental effects requiring implementation of planned and extended countermeasures. So these are major accidents. To date, there have been only 2 level 7 major accidents. First, Chernobyl nuclear power plant accident in 1986 and Fukushima Daiichi nuclear power plant accident in 2011. Here you can see the maps of cesium-137 deposition as a result of these 2 accidents in the same spatial scale. Next level from the top is the level 6, which is serious accident. So, and this serious accident means significant release of radioactive material likely to require implementation of planned countermeasures. To date, there has been only 1 level 6 serious accident. It is called so-called Kyshtym accident in 1957. So this accident was caused by thermal explosion of a tank containing high-level liquid radioactive waste which occurred in September 1957, creating what has become known as the Kështim accident. About 740 petabecquerel of radioactive material was actually released during the accident, but an estimated 90% of this radioactivity settled in the immediate vicinity of the explosion site. So means on the industrial site of Mayak. 74 petabecquerel of radioactivity was released into the atmosphere and dispersed by the wind to form the East Ural radioactive trace of about 30 to 50 kilometers width and about 300 kilometers long in northeast direction from Production Association Mayak. Here you can see the map of strontium-90 deposition as a result of this so-called Kështim accident. By the way, the city Kështim has nothing to do with this accident and has nothing to do with this release. Kështim city is just neighboring closest city to the site of Mayak. But people living in Kështim knew nothing about Mayak and what they are doing because this was top secret production. And it's located over here on the map of, let's say, Eurasia. So today we will consider three seriously contaminated areas as a result of nuclear accidents. So first is this East Ural trace, or let's say area of Production Association Mayak. Second, the Chernobyl nuclear power plant, which is located in Ukraine now. And finally, Fukushima Daiichi nuclear power plant accident and contaminated areas. So, first, we consider Production Association Mayak, which is located on South Europe near the border between Europe and Asia. It is situated on the upper reach of Kecha River, and Kecha River, Mayak is located over here on the Kecha River, and Kecha River is a part of the large basin, Kecha, Isit, Tabol, Irtysh, Ob River. And finally, the Ob River enters the Arctic Ocean, Kara Sea of the Arctic Ocean. This means that potentially this river system can bring radionuclides from Mayak site up to the Arctic Ocean. So the Mayak Production Association belongs to nowadays Russian State Corporation on Atomic Energy, Rosatom, and is located in the northern part of Chelyabinsk region, as I told you already, near the towns of Kështim and Kaslin. The enterprise was established at the end of 40s last century to produce and reprocess weapons-grade plutonium. Although Mayak is still engaged in military work, The production of weapons-grade plutonium ceased in 1987, and the enterprise has increasingly directed its technical potential towards non-military applications. By the middle of 1948, the first military reactor was installed on the site. This military reactor was in operation and generated plutonium for 39 years. It was eventually shut down in 1987. Between 1949 and 1955, 5 nuclear reactors were built at the site and 2 more reactors by 1979. In 1976, a new radiochemical plant for spent civil reactor fuel was brought into the operation. Here you can see the detailed map of Mayak location. The Mayak site itself is red area, this red area. So then we have orange. This is a health protection zone covering an area of approximately 350 square kilometers around the site. Both agricultural practices and permanent residents are forbidden within this zone, although the area is still used for research purposes. A larger area has also been designated as observation zone. This pink area is observation zone. People working at Mayak site, they live over here in city called Ozersk. So, first of all, when we are talking about radioactive contamination in Mayak area, we should distinguish 4 major releases of radioactivity to the environment from Mayak. Unfortunately, during the development of Mayak, a combination of major errors in judgment and technical failures caused severe environmental contamination in the vicinity of Mayak. So, what are actually the major incidents causing the radioactive contamination in this area? First of all, direct discharge of intermediate and low-level radioactive waste to the Teche River in 1949 to 1956. Then, discharge of low-level and intermediate-level radioactive waste to Lake Karachay on the site of Mayak. So it's over here, Lake Karachay, starting from 1951. This was started because Mayak realized that discharge to Teche River causes the contamination of river, and therefore this is a threat for the population in the lower reach of Teche River and other rivers. So then in 1957, there was a Kishtim accident, which I briefly described. And finally, wind transport of contaminated sediments from Lake Karachay in 1967. Here you can see the trace of this wind transport of the sediments from Lake Karachay. Discharges of strontium-90 and cesium-137 that occurred during the period from 1949 to 1956 have contaminated 240 square kilometers of the Teche River floodplain, with an area of 80 square kilometers contaminated at levels above 37 kilobecquerel per square meter. And they are abundant to date. About 7,500 people were evacuated from 20 settlements along the course of the Teche in 1953 to 1960, received radiation doses ranging from 35 to 1,700 millisievert. Discharges of intermediate and low-level radioactive waste to the Teche River between 1949 and 56 in amount more than 100 petabecquerel are now considered as a serious error in judgment. So here you can see the Lake Karachay. The Lake Karachay was the most contaminated lake on the earth. The Lake Karachay was originally a small, shallow natural lake, 750 meters long and 450 meters wide. Since 1951, the lake has been used as a repository for low-level and intermediate-level radioactive waste, replacing the previous practice of discharging waste into the Teche River. Here you can see the Lake Karachay in 1991, and here in 1999. So nowadays, Lake Karachay doesn't exist. Rosatom and Mayak realized the huge remediation program, and this lake was completely fulfilled with the stones and cement blocks and then covered. So, and the radiation dose rates were decreased substantially. And this was done in 2015. And from that time, there is no Lake Karachay anymore. However, the problems with groundwater still exist. And here you can see the illustration of the threat of the contamination of groundwater in the area of Lake Karachay. So here you can see the areas of radionuclides like strontium-90 and cobalt-60 in groundwater below the Lake Karachay. So the groundwater are contaminated because of filtration of radionuclides with filtration water to the groundwater. And here is the Karachay, and here is the impacted groundwater under the Lake Karachay. And this area, contaminated area, is increasing all the time. So this problem is still unsolved, and people are thinking how to solve this serious problem. So now we consider the Chernobyl accident, which happened in April 1986. Until now, the Chernobyl accident is the most severe nuclear accident in the history. As a result of the Chernobyl accident, about 85 petabecquerel of cesium-137, 54 petabecquerel of cesium-134, 1,760 petabecquerel of iodine 131, 10 petabecquerel of strontium 90, and 0.07 petabecquerel of plutonium isotopes were released into the atmosphere and transported over the long distances. So the accident at Unit 4 of the Chernobyl nuclear power plant took place shortly after midnight on 26 April of 1986. Prior to the accident, the reactor had been operated for many hours in non-design configurations in preparation for experiment on recovery of the energy in the turbine in the event of unplanned shutdown. The cause of the accident is rather complicated, but can be considered as a runaway surge in the power level that caused the water coolant to vaporize inside the reactor. This in turn caused a further increase in the power level with the resulting steam explosion that destroyed the reactor. The graphite burned for many days, and the releases of radioactive materials continued until 6th of May 1986. Here you can see the radionuclide source stem, so which is the key characteristic of any nuclear and any other accident. Here you can see on the graph the daily release rate to the atmosphere of radioactive material, excluding noble gases during the Chernobyl accident in exabecquerel per day. Exabecquerel is 10 to 18th power. As you can see, the release continued about 10 days, and after 6th of May 1986, the release dropped down significantly. Importantly, that the major releases occurred over a period of 10 days, during which there were several changes in wind direction. Here on your left, you can see the cesium-137 deposition after the Chernobyl accident over the whole Europe. And you can see that the trace after Chernobyl accident is completely different from the trace after Kyshtym accident. This was because Kyshtym accident was instantaneous, was immediate, a release was done during very short time. And actually, the trace reflect the wind direction at that time. In case of Chernobyl, the release happened during 10 days. And during these 10 days, the wind direction made a turn over 360 degrees. Here you can see how the wind turned during these 10 days. The first release was in direction northwest. And this is why first who detected the release were the Swedish monitoring system of nuclear power plants. They thought something happened on their nuclear power plant. But then when they found out, so they actually calculated where it comes from and determined that this comes from somewhere from Ukraine, most probably from Chernobyl nuclear power plant. Then the wind turned to the west, then to the east, then southeast, south, and southwest. Actually, you can see that the wind direction made such a circle, which is uh, extremely important in terms of final picture of the deposition. Also, the precipitation during that days promoted and accelerated radionuclide deposition on the surface, since wet deposition is much more efficient than dry deposition. Here you can see the deposition of strontium-90 and plutonium isotopes after the Chernobyl accident. You can see the big difference between cesium-137 deposition and deposition of these radionuclides. This is because the cesium is semi-volatile compound element, and its compounds are more or less volatile, and they evaporated at temperatures of the accident. But strontium and plutonium did not evaporate. They were, let's say, they were contained in so-called nuclear fuel particles released from the reactor. And these nuclear fuel particles, they deposited nearby to the reactor. Why strontium-90 and plutonium isotope were not so dispersed in the environment. This is the 30-kilometer zone, and most plutonium is inside 30-kilometer zone. Also, the strontium-90 a little bit go away from 30-kilometer zone, but the majority of strontium-90 is also in the 30-kilometer zone. So, therefore, the release of these nuclear fuel particles as a result of the Chernobyl accident accounts for two major features in behavior of Chernobyl origin radionuclides. Initial mobility and availability of radionuclides in near zone was lower those observed in similar condition in case of global fallout, extreme accident, and application of isotope solutions. Deposition of fuel particles on underlying surface, primarily into near zone, led to strong dependence of radiocesium initial mobility on the distance to the damaged reactor. So, here you can see the Chernobyl nuclear power plant cooling pond. And this cooling pond is one of the major water bodies that were heavily contaminated as a result of the Chernobyl accident. The cooling pond was used as a reservoir of cooling water for Chernobyl nuclear power plant reactors until 2000, when the plant was finally shut down and the cooling pond became no longer required for operational purposes. In May 2014, water pumping from Pripyat River to the cooling pond was stopped, and as a result, the water level in cooling pond began steadily declining and was reduced by more than 6 meters. By now, fuel particles deposited after the Chernobyl accident have been almost completely disintegrated in terrestrial soils. However, due to low dissolved oxygen concentration and the high pH, dissolution of fuel particles in the cooling pond sediments was significantly slower than in soils. As a result, in the cooling pond sediments, the prevailing part of the strontium-90 activity occurred in the form of fuel particles. After water level draw down part of bottom sediments exposed for atmospheric oxygen, which accelerated fuel particle dissolution and radionuclide remobilization, and therefore increasing their bioavailability. Here you can see the picture of the cooling pond in about 2018. You can see a substantial decrease of water level and a lot of, let's say, exposed sediments. So, the aftermath of the Chernobyl accident. The amount of radioactivity released during the Chernobyl accident was like that produced by atomic bombs. In the early phase after the accident, 28 people died of radiation sickness. Amongst the 134 confirmed radiation sicknesses cases, a further 11 people died in the period 1987 to 1998 from various causes, including disorder of the bone marrow, which has been linked to radiation. Also, heart disease and cirrhosis of the liver. Approximately 4,000 cases of thyroid cancer were observed in children and adolescents during the period to 2003. These were due to exposure to iodine-131 during the first weeks after the accident. Radiation exposure also potentially leads to an increased incidence of leukemia. The majority of excess leukemia cases observed in survivors of the Hiroshima and Nagasaki atomic bombs occurred within 15 years of exposure. No clear evidence of increased incidence of leukemia has been observed in population exposed to radiation from Chernobyl. So, damage to the ecosystems. It is clear that extremely high levels of radioactivity deposited during and shortly after the accident damaged the ecosystem in parts of 30 kilometers exclusion zone. In an area of so-called red forest, approximately 4 square kilometers, pine trees were killed shortly after the accident, and serious damage to trees was observed over a much large area, several tens of square kilometers. Deciduous trees were much more resistant to radiation than coniferous. Though in areas of very high radiation doses, damage to deciduous trees was also observed. Several months after the accident and in 1987, damaged trees began to recover from radiation exposure, although developmental aberrations could be observed in newly grown leaves and reduced pollen and seed viability was observed in pines. Although the direct evidence of fatalities in animals after the accident is sparse, it is likely that in the most highly contaminated areas, fatalities occurred both through direct effects of radiation and through damage to habitats. So now we briefly considered the Fukushima Daiichi nuclear power plant, which happened on 11 of March 2011. And as you probably heard, the major reason for the accident was the Great East Japan earthquake, which caused the terrible tsunami. And then the Fukushima Daiichi nuclear power plant accident happened. So here you can see the Fukushima Daiichi nuclear power plant before the accident. Here is the scheme of tsunami. Fukushima Daiichi had the anti-tsunami wall, the height of which was 5.7 meters. And this height was calculated on the basis of all previous tsunami in the history of Japan. It was never, there was no tsunami higher than 5.7 meters. However, this time in March of 2011, the height of the wave of tsunami was about 15 meters. And therefore, tsunami overcame very easily this wall and flooded the territory of the nuclear power plant. So, of course, because of the earthquake, the power lines of nuclear power plant were destroyed. Therefore, there was no electricity. Of course, the nuclear power plant had diesel generators for such cases, which were automatically switched on. However, the diesel generator were located on the knees of the building, and the building was not hermetized. Therefore, the flood covered the diesel generator and they were broken. As a result, the cooling system of the nuclear power plant was broken, and 3 operating reactors had the meltdown, and then the accident happened. And so here you can see the destroyed Fukushima Daiichi nuclear power plant right after the accident. And as a result of the accident, so here you can see in the trace after the Fukushima Daiichi nuclear power plant. This is the cesium-137 deposition. And and the next slide show you the comparison in the same scale of the, let's say, area contaminated by cesium-137 after the Chernobyl accident and in the same scale Fukushima. You can see that the levels of contamination in close-in area are similar. However, the area, impacted area is much smaller in case of Fukushima. This is because the total release of cesium-137 in case of Fukushima Daiichi nuclear power plant accident was about 5.5 times lower than in case of Chernobyl. However, there is another reason. So the Fukushima Daiichi nuclear power plant is located on the coast of Pacific Ocean. And during the accident and during the several days of release of the radioactive materials, 80% of the release was transported to the Pacific Ocean, deposited there, and diluted in the water of Pacific Ocean, which has a huge volume. And this dilution is very efficient. And only 20% of the release were transported and deposited on the land of Honshu Island. So, generally, behavior of radionuclides in the environment is governed by 2 major factors. First, radionuclide speciation in the fallout and its transformation. And second, climate and environmental characteristics determining radionuclide fate and transport. In terms of speciation, in case of Krstin accident, radionuclide were released mostly in soluble forms. In the case of Chernobyl accident, radiocesium was incorporated to great extent in so-called nuclear fuel particles, insoluble in water. Chemical forms of radiocesium resulting from the Chernobyl accident were depending on the distance from the Chernobyl nuclear power plant. Since fuel particles primarily deposited in the vicinity of the damaged reactor and radiocesium transported over large distances, was that incorporated in condensation particles that are easier soluble in water. Condensation particles are a result of condensation of evaporated cesium compounds on atmospheric dust particles. In Fukushima case, the studies have revealed spherical glassy hot particles containing, besides radiocesium, uranium, and other elements specific to nuclear fuel and reactor materials. These particles are insoluble in water, and radiocesium leaching from them is even slower than from Chernobyl fuel particles. After the nuclear accident, contaminated catchments of the rivers become a long-term source of secondary water pollution for tens of years. Here you can see heavily contaminated catchments of Dnieper and Pripyat River in Chernobyl area, and 14 river catchments contaminated in Fukushima area, which are Abakuma River, Nida River, Ukeda, Maeda, and others. So all contaminated Fukushima rivers flows towards the Pacific Ocean and bring radiocesium from contaminated catchments to the ocean. Observation, understanding underlying mechanisms and prediction of radionuclide wash-off and long-term dynamics in surface runoff and rivers is a challenge for both Chernobyl and Fukushima. Here you can see the map of annual precipitation in Japan and its dynamics during the years. Annual precipitation in Fukushima is 2 to 3 times higher than in Chernobyl and especially in Mayak. Generally, higher precipitation, higher air temperature, and steep slopes in the region promote higher wash-off of radiocesium and faster natural attenuation or self-purification as compared to the Chernobyl. Significant flooding occurs in Fukushima prefecture during typhoon season, usually from mid-August to October each year. A very rare extreme flood occurred from 6 to 11 September 2015 as a result of tropical storm Eta. During a 6 days period, more than 450 millimeters of precipitation fell in contaminated zone, which is about 1/3 of the annual norm. At the same time, this is more than annual norm in Mayak area. During the flood of September 2015, water flows washed out unsupported sections of stream banks. Also, some landslides occurred mainly on very steep slopes. So as a result, this caused substantial redistribution of radiocesium in the contaminated area. This slide demonstrates the most recent example of Typhoon Hagibis, happened in October 2019. The amount of one-day rainfall during Typhoon Hagibis in Fukushima contaminated area was up to 400 millimeters and higher, which is again the annual precipitation norm for Mayak area. By the way, this is about here you can see the forecast, but actual situation was quite close. And you can see here that about 400 millimeters fell in 24 hours in Fukushima. In some other areas, even more. So here you can see the result of the Typhoon Hagibis, a tremendous flood and with the consequences. And here you can see the Abakuma River, which flows through the Fukushima city and which is normally quite small river. But here you can see the flood and let's say floods with covering a lot of areas of floodplain. So massive flood of contaminated sediments by the rivers to the ocean took place during this typhoon. As shown by these illustrations, desorption and remobilization of radiocesium from sediments increased dissolved radiocesium concentration even in local coastal waters. Essential redistribution of radiocesium on the catchment was expected and happened. So, the aftermath of Fukushima accident. The Fukushima Daiichi accident resulted in a large release of radioactive material to the environment with the potential for exposing the local population to radiation. However, the affected population was largely protected against radiation exposure, and no one incurred a lethal dose of radiation or dose sufficiently large to cause early health effects such as tissue reaction, often referred to as deterministic effect. The stochastic health effects with the greatest potential to be manifested after the nuclear accident is thyroid cancer among children. This is the result of preferential absorption and irradiation of the thyroid gland following the intake of radioactive iodine by ingestion or inhalation. Previous experience shows that the dominant route for such intake is the ingestion of contaminated milk. In the case of the Fukushima Daiichi accident, this route was generally prevented by the implementation of controls on consumption and the estimates of thyroid dose suggest that they were generally low. It seems, therefore, that there should be not any future increase in thyroid cancers that could be attributable to radiation exposure from the Fukushima accident. Generally, in the case of the Fukushima Daiichi nuclear power plant accident, the inferred lifetime risk values are extremely low and well below the levels for which effects have been observed. And the hypothetical numbers of cancer cases calculated by using the risk model are a small fraction of the expected number of spontaneous cases. There is a little likelihood of discerning an increase in cancer due to radiation from the accident at the Fukushima Daiichi nuclear power plant in general population or among emergency workers in the future. So, to the end, I would like to recommend our book series, Behavior of Radionuclides in the Environment. Two first volumes of the book have been published by Springer in 2020 and were devoted. The first volume was devoted to Karachay Lake at Mayak in Russia, and the second volume was devoted to Chernobyl. Volume 3 of the book is devoted to Fukushima Daiichi nuclear power plants and have been just published last year. So for first two volumes, we edited together with Stepan Kalmakov, who is the leader of the Radiochemistry division in Chemical Department of Moscow State University. So thank you very much for your attention, and I will be happy to answer your questions. Are there any questions?
Yes, I have a question.
Yes, please.
First of all, thank you very much for your presentation. It was very interesting for me. My question is on, there was a slide where you showed how radionuclides are transported. And then for the Kishtim accident, you said the cesium was soluble. And for the Chernobyl accident, it was insoluble. And then my question is, how can we determine, or is there a determined way of knowing how the radionuclides are going to be transported depending on where they are produced? I ask this question because my research is mainly focused on how potassium-40 can be used to reduce the transfer rate of cesium-137 and strontium-90 in plant uptake. And from the little stuff that I read, these radionuclides are mainly produced in nuclear power plants, and I thought they were soluble before listening to your lecture. So that's my question.
Okay. So very good question. And yes. Yeah. Sorry. Okay, this is a very good question. Yeah. First of all, yeah, the state or speciation or chemical form of radionuclide entering the environment is the key characteristic, because the fate of radionuclide and transport of radionuclide in the future will substantially depend on the speciation. So, in all three cases, we have considered today the speciation of radiocesium was substantially different. Radiocesium and radiostrontium. Why I talked less about radiostrontium? Because in case of Fukushima, we don't have a release of strontium. We don't have any substantial concentration of strontium. The Fukushima is, we can say Fukushima is cesium accident. So cesium is common for all three contaminated areas. But its initial speciation was completely different. In case of Kishtim accident or this explosion of the tank with liquid radioactive waste, cesium existed there as a soluble salts, so as a soluble compounds. In case of Chernobyl, because cesium is semi-volatile element, so during the accident, the temperature in reactor was about 2000 degrees Celsius. This is very high temperature. And cesium compounds could evaporate. And but also cesium remained in the nuclear fuel. And therefore, when it was released into the atmosphere, cesium was a part of condensation particles, which were produced by the condensation of vapors of cesium compounds on the atmospheric dust. And also cesium was a part of nuclear fuel particles. So the ratio is about 75% of cesium were released as fuel particles, and only 25% were released in evaporated form, and then they started to be condensation particles. Condensation particles are easily soluble and therefore bioavailable, but fuel particles are in general insoluble because this is nuclear fuel. As you know, nuclear fuel is uranium dioxide. This is quite insoluble compound. However, these fuel particles, uranium dioxide, are oxidizing in the environment by atmospheric oxygen. And it is oxidizing up to the uranium 3 oxide or uranium 2 plus X. Yeah, more than all these uranium 3 oxides and uranium O2 plus X, they are more soluble than uranium dioxide. Therefore, with time, we have decomposition of fuel particles, the oxidation and mobilization of radiocesium from fuel particles. So the time scale of this process of fuel particle decomposition and mobilization of radiocesium is about, in general, in average, is about 2 years. So this means that after 10 years, after the accident, actually in soils, most of the fuel particles were decomposed and radionuclide leached from these fuel particles. In case of Fukushima, we had also 2 types of particles. First, such similar to condensation particles, and another ones, so-called cesium balls or glassy hot particles, which were generated inside the reactor, and they were very insoluble in water. And moreover, the time scale of their decomposition in the environment even longer than fuel particles. Because what is the glassy particles? This is silicates. This is like a glass, yeah? And glass is not oxidized in the environment and can stay in the environment for very long time. And time scale of leaching of radionuclides from glassy hot particles in Fukushima is at least 10 years or even longer. So, and all these facts, actually, they impact on fate and transport and bioavailability of radionuclides in this area. And when we analyze this in details, we should take this into account. What is the technique to separate different chemical forms or speciation? Actually, for a long time, the basic techniques to separate this is the sequential extractions. For example, you can extract radionuclides from soil or sediments or whatever, first by water, then by neutral salt. For example, very often the ammonium acetate, 1 mole ammonium acetate solution is used for that. So it is considered that the so-called exchangeable form of radionuclide is extracted by this extraction step. Also, you can use first slight and then strong acids until fluoric acid. Fluoric acid is the only acid which destroys minerals, let's say geological minerals, and therefore you can extract these radionuclides very strongly bound to the let's say geological even media, or let's say clay particles and so on. Did I answer your questions? Hello.
Yes, thank you very much.
Okay, my pleasure. Are
Thank
there
you.
any more questions?
Thank you very much for your presentation. My name is Samuel, and my question is, you talk about atmosphere contamination, and you made mention of these contaminations can go as high to the stratosphere. I want to know if it can go beyond the stratosphere, maybe to the mesosphere and thermosphere, when it comes to radiation contamination in the atmosphere.
Say it again. Which atmospheric layer you are interested in? So there is a troposphere, there is a stratosphere, there is a thermosphere, there is an ionosphere. Which one you are interested in?
You made mention that it can get to the stratosphere. So my question is, can it go beyond the stratosphere? Maybe to the mesosphere?
Mesosphere. No, it's too high. It's too high. Generally, it was, let's say, it was proved that it goes up to the stratosphere, but at the stratosphere is, due to the temperature change, is more or less isolated. There is no easy mixing with the troposphere. And these particles, and also the pressure in the stratosphere is much lower than in the, let's say, lower layers of the troposphere. And therefore, in this condition, these particles, they very efficiently dispersed over the globe. So you mean, what is the point? You know, the nuclear tests and explosions were in, let's say, specific locations. However, the global fallout received all over the world. Why? Because of that fact that the particles, radioactive particles, they reached the stratosphere, then they, let's say, dispersed along the stratosphere and then slowly deposited on the surface. So therefore, the global fallout is more or less homogeneously distributed over the, let's say, at least on the level of hemisphere. For example, total deposition on northern hemisphere is higher than total deposition in southern hemisphere. But this is just because of the total amount of nuclear weapons tests in northern hemisphere was much larger than in southern hemisphere. And as I understand, the northern and southern hemisphere, they are not very well mixed, although there is some exchange, of course, but generally deposition in southern hemisphere is lower as compared with northern hemisphere. But if we are talking about the northern hemisphere, so the deposition of global fallout is more or less homogeneous. It does not depend how close is it for the with the let's say nuclear test sites or so, more or less homogeneous, and the concentrations, let's say in Europe, are similar to the concentrations in for global fallout in Asia and so on. Okay, did I answer your questions?
Yes, please. Thank you very much.
Okay. Okay.
Thank you very much, Professor, for your nice presentation. My question goes to one of the accidents, Kistim accident. It's said, or you said, that the accident starts from liquid waste in a tanker. So
Yes.
do we know the source and the nature of this liquid waste, plus what actually triggered the explosion?
Okay. Okay. Very good question. Very good question. The situation in reprocessing plants in Soviet Union and in US was quite similar. So the radioactive waste, liquid radioactive waste, you understand where the liquid radioactive waste come from. If you extract plutonium for let's say nuclear weapons grade plutonium from nuclear fuel, you do it with strong acids and so on. So therefore, after extraction and using plutonium or whatever you need, you have a lot of liquids with high concentrations of very different radionuclides, very different fission products. So generally, people at reprocessing plants do create or produce a lot of liquid radioactive waste, which is very dangerous because it is very radioactive, and therefore there is a problem what to do with this radioactive waste. First, depending on activity, this radioactive waste is split on low level, intermediate level, and high level. High level radioactive waste is very much radioactive, dangerous. So no way to discharge it somewhere. So therefore, the high-level radioactive waste is they put high-level radioactive waste in tanks, very big tanks, which were located underground. So this system was realized in Mayak, and even before, it was realized on the Hanford site. Hanford site is the reprocessing site in US, in Washington state, where actually the first in the world plutonium was produced. So this large tank is, let's say, closed with the Lee. And in Mayak, what happened in Mayak? So first of all, these radioactive waste are quite, let's say, reactive liquids, yeah? And when they mixed, let's say, just occasionally without proper attention, they can react with each other. And such kind of chemical reaction, exothermic chemical reaction, happened in that tank at Mayak. So the reaction was so strong and the heat release was so powerful that the tank was exploded. So the cap of the tank was removed, and all this material which was in the tank and the influence of the temperature was released. So this accident in Mayak in 1957 was not reactor accident. This was very specific event with high level radioactive waste. What was happened with low and intermediate level radioactive waste? I told you, first, this radioactive waste in 1949 was discharged to Techa River. So, and contaminated Techa River very seriously. So when they realized, you should take into account that in 40s and 50s, nobody knew about, let's say, threats of radioactive contamination and so on. There was not such a problem. So also at that time, Soviet Union was in the rush because the Cold War, you know, after the Second World War, the Cold War started, and US demonstrated that they have atomic bomb in 1945, and Soviet Union decided that they should create atomic bomb as soon as possible. This was nuclear rush. So this is why this Mayak was located far away from Moscow and so on. And and this site was kept as a top secret. So they didn't take into account the possible environmental consequences properly, not just because they didn't care about it. They didn't know anything, or they knew almost nothing about how radionuclide behave in the environment, what is the threat for ecosystems, and so on. But when they discharged during about 1 or 2 years, they realized there is a problem that ordinary people who know nothing about this mayak and what they are doing, they are under threat. Therefore, they started to discharge this low level and intermediate level radioactive waste to Karachai Lake, Lake Karachai, which is located inside the industrial site of Mayak. And therefore, nobody had access to this Lake Karachai. And they contaminated Lake Karachai tremendously. So it was very difficult. It was impossible just to stay on the bank of this lake. The dose rate was extremely high, even on the bank of this lake. Did I answer your questions?
Thank you, sir, Mr. Kinano.
Yeah, my pleasure.
Okay, we haven't no time. Thank you very much for your lecture.
Okay. Okay, thank you very much. And I wish all the students successful end of your school and useful exercise and useful lectures. Thank you very much for your attention. We need to break now.
Да. Well, let's start. Time is run out. Today my lecture will be more informative, and it's devoted to separation techniques in radiochemistry, with emphasis on isolation of radionuclides from irradiated target. Most of my examples will be about radionuclides that are close to radiopharmaceutical chemistry. So, in general, about separation methods and techniques. In chemistry, when we want to separate two different substances, first of all, we should use two-phase systems, heterogeneous systems, because they can be mechanically separated, and we should make some chemical process that looks like redistribution or distribution between these two phases. Depends on the type of phases, some techniques are arised. First of all, liquid-solid systems, it's a precipitation and co-precipitation. Also, it's a chromatography. I think that chromatography is the most widespread technique in chemistry, in all of branches of chemistry. Another important technique is the liquid-liquid extraction. It's also called solvent extraction. And in case when we work with gases, this is gases solid system for gas absorption. In case of radiochemistry, in case of, I think, first point here is about radiometric problems. Maybe you already heard or will be hold a lecture on it. Analysis of so-called difficult to measurement radionuclides. Sometimes we need to separate one radionuclide to be sure that we can measure another radionuclide, or it's also important, sometimes our radionuclides are presented in some difficult matrix for analysis, and before measurement, we should remove this radionuclide from sample matrix or another interfering nuclides. Also, another problem is removal of decay progeny. We have this problem when we have some hot targets with high activity, but the radionuclide of our interest is just a small part of this radioactivity. And to work safely with it, we should first remove this radionuclide. And another, I think, the biggest issue is purification of radionuclide. We will see lots of examples where it's really important, where before we can use it as a medical radionuclide, we should make a proper purification of it. Let's start from precipitation and co-precipitation. So maybe you remember that when we want to understand will be precipitate form, we should look at so-called solubility product constant. This is the value. Well, we should compare our the concentration of our salt or another compound. We should product its concentration in the power of stoichiometric coefficients. And if this product is higher than solubility product, precipitation can occur. In another case, when it's lower, there will be no precipitation. And here are some examples of these solubility products for different inorganic salts. You can see that they are very, very low. Their powers, for example, in copper sulfide is about minus 39. What does it mean? It means that when we mix up some substances, when they have micro quantities, of course, we will have precipitation. But what is issue in radiochemistry? For example, let's take a look on this isotope of silver, 105. It has a little bit short half-life time, 41 days. That means that when we work with a quite active solution with 1 megabecquerel per liter, if we want to try recalculate on a concentration of silver in this solution, it will be about 10 in power of minus 11. And if we look on the solubility product, you can see that even we take 10 mole per liter chloric acid, there will be no precipitation. What we should do in this case? We should use so-called carrier. It's a stable, in general case, it's a radionuclide that we can take in a big concentration, add to this solution, and after that, co-precipitation can occur. So during this process, we will have precipitation of radionuclide with micro quantity of stable substance. But of course, there are different types of carriers because they're different and difficult situation. First situation from previous slide is easy because we have a stable isotopes for a silver. So we can use stable salt, stable isotope, and we can remove radioactive silver from the solution. But another example, specific non-isotopic carrier. Of course, there are many radionuclides that have no stable isotopes. For example, radium sulfate. It has the same problem, very low concentration in solution. And if we want to make a precipitate with it, we should use some kind of chemical analog of the radium cation. The closest from chemical point of view is barium. And we add barium, we add sulfate, and we obtained precipitate with a radium in it. And the most non-selective way, it's non-specific and non-isotopic carrier. We use compound with really different chemical properties. For example, if we take hydroxide of iron, precipitating in solution when we have radionuclides, almost all, for example, actinides will go to this precipitate. It has a very high surface, and because of it, it can easily catch all the radionuclides, and especially actinides. And when we're talking about where it can be used for some useful things, I think the most proper thing when we want to concentrate some radionuclides from aqueous solution. For example, if we take seawater for analysis, we take really big samples. For example, hundreds of liters of this seawater, and it's quite difficult to take them from sea to the lab. You need to take not one sample, you need to take dozens of samples. It's really high weight. But you can use precipitation to make a compact sample from this 100 liters sample of seawater. And for this reason, as I told you, hydroxide of iron is a real good co-precipitator. Another example is a calcium phosphate and some kind more, I think, more simple compounds such as oxides and fluorides of lanthanides. Also, what we can obtain by precipitation. First one is the removal of interfering radionuclides, but it it really depends on the type of your sample, of nature of these radionuclides. Another also important point is the separation from sample matrices. It looks like close for the first issue, and as I show you, is pre-concentration or concentration of nuclide of interest for another chemical procedures or for radiometric analysis. And also some examples. There's two, I think, different examples from the previous slide. For example, if we want to catch carbon-14, we can use carbonate of calcium. For chloride ions, it's also chloride of silver. And another examples for cations. One more examples, you can see that in most cases, this is inorganic salts. One example of dimethylglyoxime for nickel. One more interesting example is for cesium-137. It's a quite difficult inorganic salt. The precipitation occurs by exchange of cesium with potassium in this compound. And another very important note here is example for alpha spectrometry. Alpha spectrometry is one of the difficult technique for lab from point of view of practical procedures. If we want to obtain high quality alpha spectrum, we should make a very, very thin sample, and it's quite a bit easy to make it up by co-precipitation with some of the inorganic salts with use of special filtering system. These filters, they already have fluoride of cerium in the composition, and because of interaction between of fluoride of cerium in solution with fluoride of cerium, these filters, we obtained a good layer for alpha measurements. So, pros of precipitation. We can say that it's a quantitative process. In many times, we obtained all of the radionuclides from solution in our precipitate. In general, here we use relatively simple compounds, simple reagents to precipitate something. You will see, we will further see solvent extraction and chromatography. The reagents there are quite difficult in comparison with precipitation. Also, we in general, we can obtain high degree of concentration in one experiment. And also, this technique can be scaled up from milligrams of micrograms in case of radionuclides to industrial amounts of substances, kilograms, hundreds of kilograms, and so on. And some minuses of this technique. First of all, I really believe that everyone who make precipitation of different substances know that it's really time consuming. You wait when all of your solution will go through the filter. If we obtained a high amount of precipitate, it goes slower and slower and slower. So that's why it's a time consuming technique. Another problem, of course, if we want to precipitate radionuclide, we have no idea beside of use of carrier. But of course, in sometimes carrier is problem for further chemical procedures. Also, in general, it's not very technological technique. It's okay for lab. It's okay for something between lab and industry, but in industry, in case of, for example, selectively things, it's a difficult technique. And of course, precipitation, I think, is non-selective process. If you have wide range of radionuclides, wide range of metal cations, a little part of them always go to the precipitate. It depends on the task you want to solve. But if you want to have high purity radionuclide or metal cation after precipitation, in general, we should use another technique to purify our radionuclide of the interest. So it was about precipitation and co-precipitation. Now we are going to another technique, solvent extraction or liquid-liquid extraction. In general, not in radiochemistry, solvent extraction is widely used in analytical chemistry, in organic chemistry to purify organic compounds, and biochemistry. And also, it easily can be scaled up to industry amounts, food biology technique, and hydrometallurgy. It's a very important branch of separation because by this process we obtain pure metals that are really useful in other industries. For example, rare earth elements, for example, uranium and plutonium during Purix process, and so on. So this is separating funnel. It's a special lab equipment to conduct solvent extraction. In general, there are two phases. One of them is organic or oil phase. It's a non-polar, and we try to extract some compounds from water on it. Of course, if we use hydrocarbons, it has less dense than water, and because of it, organic phase is higher than aqueous phase in this separating funnel. Another example, when we use chloroform, it has high density and it goes down. So, and by this and как экран будет? Valve, yes, thank you so much. By this valve, you can remove first phase and after that second phase. That's how separation occurs. And what happened in this separating funnel or some kind of industrial extractor? First, one more time, solvent extraction is a distribution or redistribution of component between two immiscible liquids. And in the beginning, I think always we have aqueous phase with a component of interest. Their mass transfer go on by contact of phases. We should obtain a good emulsion for it by shaking, for example. And at the end, we separate these phases because they are unmixable. We can mechanically separate them. And of course, some nomenclature here. From point of organic phase, in general case, it's composed by extractant. It's a special compound. They will bind your cations. And we also used some kind of diluent to make volume of this organic phase. Initial solution, sometimes called feed solution. After the extraction, we obtained raffinate. It's an aqueous phase after extraction, and extract its organic phase that have compound of interest. Of course, usually scientists, laborants, and so on, they need their compound back to go back to the aqueous phase, and this process called back extraction or stripping. And here we obtain back extract. And also, when we're talking about separation techniques, usually we in first step we extract both of these compounds and after that, by changing the condition of aqueous phase, we can take back only one of these compounds. And this process called scrubbing. And here I think in case of precipitation, the chemistry behind this process is relatively easy to understand. And in case of solvent extraction, we should have a brief look to the mechanism of this process. And first one is a so-called physical redistribution. Driving force of this mechanism is solvation by organic solvent. There are many compounds that have low solubility in aqueous phase. It's low, but it is. And high solubility in the organic phase. For example, extraction of iodine in toluene. Maybe you see this experiment. We have a brown solution of iodine in aqueous phase. Sometimes it can be really pale brown color. And after contact with the toluene becomes pink, bright pink color. It's easy to see how extraction go on. And it's work because non-polar compounds can be easily solvated by organic solvents. And by this mechanism, we can extract weakly polar organic molecules, halogens, and some high symmetric molecules with zero dipole moment. And this mechanism is usually used in organic chemistry because organic chemistry deals with the non-polar substances in general. And also another important point that by this mechanism, not only organic compounds can go to the organic phase, but also water can go to the organic phase, and parts of the diluent also can go to the aqueous phase. So during this process, a redistribution of all components can go on. And it's important and even important in radiopharmaceutical chemistry because we should obtain our radionuclide with no radioactive another radioactive substances, and also without any interfering compounds such as organic can be. So solvate mechanism. In this case, we have a special compound that can bind cations in aqueous phase. In general, there are 2 points that organic should have. First one is groups that can coordinate metal cations. It should have oxygen or nitrogen or sulfur in its composition, and it has no charge, and it can be and it's soluble in the organic phase. By this mechanism, we can extract metal salts and acids, and here it is equation by which we can imagine the process that goes in the two-phase system. Well, there one difference between equation in chemistry and equation in a two-phase system. Here we add in what phase we have the compound, for example, ligand in the organic phase, this salt in the aqueous phase, and after extraction we obtained the complex compound in the organic phase. Also, this is looks like solid mechanism, but sometimes in some classifications, scientists say that there's a very neighboring mechanism called hydrate solvate mechanism. It occurs when we can register water molecules in the complex compound in the organic phase. And mostly by this mechanism, extraction is going on for metalloids, for example, they're here, and all of these metals, they can form such type of acids, complex acids. And here it is some examples of extractant that can work by solvent mechanism. First one, the tributyl phosphate. I think it's the most usable organic compound in the radiochemistry. By this compound, uranium and plutonium extracts during Purex processes. It also used in other branches of hydrometallurgy. For example, separation and isolation of rare earth elements goes with this extractant, and another problems, for example, isolation of cobalt and another rare metals. And it's another molecule, it's called phosphinoxide. It have very powerful extraction efficiency compared with the TBP, but it doesn't work in acid solutions. Another example that have oxygen coordination group with carbons, it's a methyl-isobutyl ketone. Previously, before TBP, it also was used for reprocessing of spent nuclear fuel, and another nitrogen-containing extractant is a triactylamine. And more complex compounds for isolation of radionuclides. This is so-called crown ethers. It's widely used for separation of alkaline and alkaline earth metals. They have so-called size effect. By variation of number of carbons in the structure of molecule, we can adjust a radius of this cavity for certain alkaline or alkaline earth metals. And another more huge microcyclic compound, so-called calyx 4 arenes. There, for now, I think there are calyx 8 arenes, so they have 8 aromatic groups in their composition. Many options for synthetic modification to make a special extractant for certain cation in presence of another cation, in presence of different radionuclides. And another next mechanism is a cation exchange mechanism. First of all, driving force here is the formation of organosoluble salt. And extractant here is the organosoluble acid. The most widespread type of extractants is the phosphor-containing acids. They have different oxidation state of phosphormanate, phosphoric, phosphonic, and phosphinic. In less extent, here use carboxylic acids. And by this mechanism, we can extract metal cations and sometimes metal salts. Their mechanism is more difficult than in case of solvate mechanism. 2 points here. 1 point, then if we use organic soluble acids in non-polar solution, they makes dimers. They contact by hydrogen bonds and works like dimer. And we should mention it in the equilibrium equation for this process. Another point, it's called cation exchange mechanism. It means if we take in the organic phase cation with a charge, the equal amount of protons will go to the aqueous phase. It means that we can rule this mechanism by adjustment, increase or decrease of protons in the initial aqueous phase, and also we can use increasing of proton concentration to make a back extraction. Lots of protons, no extraction, back extraction. And the complex compound have different bonds and structure. They're hydrogen bonds, they're ionic bonds, and coordination bonds in the structure of this compound. And more certain type of extractants like a TBP in solvate mechanism, the example of widespread cation exchange extractant. It's a D2-ethyl phosphoric acid. I think in Wikipedia you can find about 6 acronyms for this compound, but in literature the main one is HDHP and DIHPA. Another widespread example is more complicated name. I don't want to name it, but it's called PC88A or HEHEP. Yes. And a minor from point of view of usage is a mixture of carboxylic acids. It's called versatic 10. It's a byproduct from reprocessing of oil, and it can be used. It can be obtained in the high amount. So it's sometimes, from economical point of view, it's okay to use this extractant, but it has very low effectiveness. And of course, if we have cation exchange mechanism, we have also an ion exchange mechanism. Here, driving force is the same as the formation of organosoluble salt, but by exchange of anions. And if you try to understand, can this molecule acts as an ion exchanger, we should find organic cation. And the more spread type of extractant here is a quaternary ammonium basis, and in less extent is a cation of pyridinium and imidazolium. This is in general the components of so-called ionic liquids. And by this mechanism, we can extract anions. But there's one important point here from radiochemistry. Sometimes some scientists think this is perthictite anion is the most important metals that presented in solution in anionic form. Technetium is very important radionuclide in case of nuclear medicine from one point of view, but another is a radionuclide that make reprocessing of spent nuclear fuel is really difficult. And of course, anion complexes of different radionuclides of different metals. It's important thing here that we can play with this mechanism by use of different anions. The extraction in case of nitrates, the extraction in presence of chloride ions can be different. And by this, we can adjust condition to obtain the target result. And there, this is equilibria that goes during anion exchange mechanism. So what's problem can be during solvent extraction? First one is third phase formation. Solvent extraction works well only when we have two phases, in the beginning of process and in the end of the process. If we obtained third phase, it can be a very stable emulsion, or it also can be precipitating two-phase system. We can conclude that this system doesn't work for separation of metal of radionuclides. Sorry. Well, and we want, of course, we want to use some parameters for describing of our process, and they have a very simple calculation. First one, when we want to describe extraction, we use so-called distribution coefficient or distribution ratio. It is easily calculated by use of equilibrium concentration of component in organic phase divided by concentration of component in aqueous phase. It has a very simple physical meaning. If this ratio is higher than 1, the process goes. It means that we obtained a more compound in organic phase than in aqueous phase. And in turn, if this is lower than 1, the biggest part of component is still in aqueous phase. The extraction is non-effective. Also, we can calculate so-called extraction rate. It's a percentage part of the initial concentration that goes to the organic phase. And of course, we talk about separation. For separation, to describe separation, we use separation factor, or in Russian literature, we use beta for this parameter. And it calculates as we should divide distribution ratio of one of the component by another, and easily see if distribution ratio are the same for both components, the separation factor equals to what? 1, and there is no separation. For example, if we try, there are some examples, to separate isotopes by chemical procedure, this separation factor is 1.01. It's not really equal to 1. It's really tiny differences between chemical properties of isotopes, and sometimes it can be used for separation. And in general, in the scientific literature, one can say that good separation if we have separation factor about 1000. But sometimes in radiochemistry, not only in, for example, rare earths purification, separation factors can be 1.5. And it's enough for industrial scale implementation of such solvent extraction system. And also, mainly in industry, we also use so-called enrichment factor that show how ratios between component decreases or increases during separation process. And there are some rules what coefficients we should have for certain separation system to have very efficient, effective separation to species. You can find here. So one component should have a high distribution ratio, higher than 1. Another component should have distribution ratio lower than 1. And sometimes it's say that product of this distribution ratio can be equal to 1, but I think sometimes it's really difficult to find such a separation system to have this coefficient. And what can affect solvent extraction process? First effect, so it's called salting out effect. How it works, how it looks like. For example, here's isotherm of extraction. It's a dependence of concentration in organic phase to a concentration in aqueous phase. Here we extract uranium by TBP in presence of sodium nitrate. And you can see that if we have no salting out agent, the isotherm, I think, goes slow. And if we add a high amount of salting out agent, it have a very high growth. It means that even if we have about 40 grams per liter of uranium, even in this, we have a high amount of uranium in organic phase. Already we have the full capacity of the organic phase. And if we have no salting out agent to obtain this amount of uranium in organic phase, we should use a very concentrated solution of uranium. So how and what are the reason for this mechanism? First of all, is a shift of chemical equilibrium towards formation of complex, because we have nitrates, for example, and ions in the composition of complex. If we add much amount of anions here, the equilibrium shifts to the complex compound. And another point here, of course, when cations are presented in the aqueous phase, they are not swallowing that. It form aqueous complexes with molecules of water. And first part of extraction is removing of molecules of water from this cation. And if we help this process, we can increase the solvent extraction. And also, if we add salt in the aqueous phase, some water molecules from these compounds will go to the anions and cations of salting out agent. And that's why the extraction goes more efficient. So that's why salting out leads to the increase of distribution ratios and coefficients. So let's go on the effect of acidity. As effect of acidity is really emphasized for cation exchangers such as HDHP, and the dependence of distribution ratio on concentration of nitric acid, for example, is really difficult. We have several maxima, several minimum here. How it works? First of all, in case of a wide range of the elements such as molybdenum, when we have solutions with high pH, most of the elements form hydrolysis species, and these species are not extractable. We should have cation form of our metal. In this case, extraction goes on. And if we make this solution more acid, add nitric acid, pH goes lower and extraction is growing. But if we add too much nitric acid, extractant is protonated. It extracts protons, not metals, and extraction goes down. But in a very concentrated nitric acid solution, we obtain change of mechanism from cation exchange to solvate. So HDHP molecule can act like TBP in a very high acidic solution. And here we obtained effect of salting out. So one more time, when we deal with cation exchanger and extraction, they have a really difficult nature, difficult extraction behavior. Every time when you think that in case of isolation of some radionuclides from target solution, we should keep in mind that in case of cation exchanger, it can be really difficult to find proper condition of separation. And solvent extraction pros and cons. Pros. This process can be rapid, this process can be efficient, and can be very selective. Selectivity of process depends on the type of extractant, so based in our choice of extractant. We should see what the condition of our solution, what the target radionuclides, what the interfering radionuclides, and based on this, we should choose the proper extractant. This process is widely used in extraction, in hydrometallurgy, in biotechnology, food production, and so on. In case of radionuclides, as we see, in most cases, radionuclides have very low concentrations, and in the region of low concentration, distribution ratios are independent from radionuclide concentration. And also, we can conduct back extraction into aqueous phase, and during these processes we can concentrate the radionuclide of interest. And of course, cons. During solvent extraction, we use toxic or flammable solvents. I think in lab, it's not big problem, but when we scale up to industry process, you use high amounts of toxic compound, it's bad idea because we are talking about nuclear medicine radionuclides. And another, if they're flammable, it's a fire danger when we use such kind of systems. Another point here, if we works with low separation factors, for example, from 1 to 10, we should use multiple extraction processes, and in the lab it's difficult. They're difficult for lab equipment. It's difficult to make this process in your lab. And of course, if we contact organic with the radionuclides, after that we obtained large volume of radioactive organic wastes, and even there no radioactivity, we also obtained organic wastes. And another point is the composition of organic solvent. There are many examples when we use in industrial scale, for example, different ways of production of solvent, even of hydrocarbons. There from sample to sample, we can obtain different extraction properties. And the biggest branch of separation techniques is a chromatography. It's have the biggest definition because 2 points, I think. 1 point, this is dynamic process. We will see a picture of it, but please mark, this is dynamic process. And the phases here, in case of precipitation, we have aqueous phase, solid phase. In solvent extraction, two liquid phases. And here we can have a really different phases. We can use solid liquid system, we can use gas solid system, liquid gas system, and so on and so on and so on. And in case of radiochemistry, because in general we works with the cations or anions, the most spread subgroup of chromatography methods is ion exchange chromatography. It based on the exchange of anions from sorbent to the solution. Every time we're talking about from fundamental point of view on electrostatic attraction between sorbent and cation. And of course, we have 2 types, cation exchange and anion exchange. So how in general all chromatography methods works? We have 2 phases. We also have redistribution of our components between these 2 phases. And here we see just a static mode. It looks like close to solvent extraction, really. 2 phases, 1 component, the same. And after that, in static mode, we bring the contact between these phases, and we have distribution of components between these phases. But in case of chromatography, it's very easy to make this process dynamic, as a dynamic process. So we can use gravity. Our mobile phase will go through the chromatograph column, and in each part of this column we can obtain 1 static mode. It means that by simple lab equipment we make multiplying of static mode, and by this we obtain high efficient from separation point of view. So repeated multiple time static process give us efficiency of separation. about liquid extraction, solvent extraction. In general, the idea of dynamic process and solvent extraction is the same, but we can't use gravity. We should push up organic and aqueous phase in countercurrent. You need pumps, you need a special equipment to make it in the lab, but sometimes in general, in case of industry problems, there's only one way, is a solvent extraction in dynamic mode. Well, another GIF, how it works in dynamics. We put two components at the beginning of column, and based on the interaction with sorbent, the different velocity of process can occur. Оля, а сколько у нас времени есть? 5 минут. We have just... Okay. I try to speed up, but I have 24 slides more. It's just half. But you can, if you want to go to it, it's okay. I understand you. Okay, so if we collect the fractions from here and measure the concentration of component, we will have such profile. It means that with low amount, with low volume of diluent, we have the first blue component, and with the high amounts, we have red component. But this method of chromatography is it's called frontal, but in case of radiochemistry, it's not very useful, because first you should collect your first component, and after that take another component, and in general you don't know where it goes, where the first component is left, and we should wait for another component. And in general, we use so-called eluent chromatography. Firstly, we put all of the anions in the column, and after that, we use different solution with different concentration of acids, different salting out agents to remove the radionuclide of interest. Sometimes displacement chromatography is useful. It's also, we put all of cations in the column, and after that we add special cations that remove cations of interest. It works, I think, rarely. And general, it's eluent, so optimization of conditions. By optimization of conditions, we will have several radionuclides with high purity. What sorbent is? First of all, it also can be named stationary phase. We have inert support to the frame, and in this frame we put functional groups. And in general, this inert support is a polymer. For example, here you can see a copolymer of styrene and divinylbenzene. And by different chemical procedures, we put functional groups on it, and it looks like this sponge, I can name it. And we say that in general, cation and anion exchange chromatography, but we will see also example so-called extraction chromatography. And different functional groups for different tasks. For example, the most spread group to modify the 3D polymer is a sulfonate group. I think the biggest part of sorbents for the cation exchange works by this group. And for anion exchange resins, we use quaternary imine groups. And this is a picture of the resin. And how it looks like the sulfonated copolymer. It have such kind of groups on it, sulfur groups. and also some parameters that we can calculate to describe the effectiveness of separation properties of our resins. It looks like the distribution ratios in solvent extraction, but we should take into account ratio between volume of aqueous phase and of mass of the sorbent. And the same for separation factor. Well, pros of ion exchange. It's a simple and efficient method. One more time, it's a dynamic method that can be easily conducted in every lab. You should even take a pen, remove inner part of it, put sorbent in it, it will be a chromatography column. Also, this method is a wide range from lab to the industrial scale, but with some restrictions, but it's a very special cases. Because of it's a dynamic process, we have high chemical recovery of a target radionuclide. And in case of separation in lab, I think it's the best technique to isolate nuclear medicine radionuclide. Cons. The first cons, I think, in general cons, if you're carrying out every chemical reaction, you should control all of conditions of this reaction, and in case of ion exchange, is a pH control. Sometimes, in case of radiochemistry, especially, we generates problematic secondary waste. Sorbent, after the contact with the radionuclides, with the radioactivity, it becomes a radioactive waste. Of course, sometimes for some tasks, if this task is difficult, we cannot find proper ion exchanger to separate some of radionuclides. And it's very discussable cons, because here we see less selective if we compare it to solvent extraction or extraction chromatography. It's true, but because of dynamic process, sometimes selectivity is really higher than in solvent extraction if we're talking about solvent extraction in context of static mode. And if we want to combine pros of extraction and solvent extraction and chromatography, we can use extractant as a functional groups. And efficiency of chromatography is a dynamic process, but with low selectivity. If we add here selectivity of extractants, but it's difficult to make a dynamic process, we will have technique with high separation efficiency and with the efficiency and the total efficiency in production of radionuclide. Another fundamentally important thing that the dependencies that we can obtain during solvent extraction, during extraction chromatography will be the same. We can make solvent extraction test to understand what we should wait from chromatography test. In case of extraction chromatography, first of all, the main problem is here how we put extractant on the non-mobile inert support. And in general, the bonds between the extractant and solid support is weak. It's a main problem of extraction chromatography because sometimes our solutions that we use to isolate radionuclides, they're really aggressive. We can have acids, oxidizers, activity, and because of it, we should make a really good choice of inert support to obtain good result from separation. And how it looks like in the lab. Every time when we work with the chromatography, we also have problem of moving of aqueous phase in the sorbent. And because of it, we should use a special box with a vacuum in it, with a pump, to speed up this process. And all of these resins in general, they're commercially available. And in many times, the manufacturer that makes this resins, the name of this resins highlights the purpose of this resins. You can easily see this is nickel resin for isolation of nickel, and so on, so on, so on, so on. So it's really commercial products that can be easily to buy. And well, I think it's really big slides. So мы же отправляем презентации. Супер. I think this is a very specific slides for different reasons, and I think you can by yourself take a look on them if you want to understand is it resin is okay for your case and so on. I will go next. And pros and cons, extraction chromatography. This is really so-called state-of-the-art method that combine two methods in one. We can use individual columns for each radionuclide. It has high selectivity, high productivity, but the resins is expensive compared to the precipitation, solvent extraction, compared to the ion exchanger is expensive. Reason bleeding, as I say, weak bonds between extractants and the support. That means that if we make lots of separation processes, after that the efficiency of column will be decreased. Also toxic components, but I think in case of radionuclides it's not big problem because we work with the activity. And limited capacity is a general problem of chromatography when we compare chromatography with the precipitation of solvent extraction. In the case of later, we can work with a high concentration of metals of radionuclides. In the case of chromatography, we have lots of problem with the capacity, maximum capacity of chromatography resin. And just 5 real cases of using of separation techniques. First one is a process for isolation of actinium-225 and simultaneous isolation of radium-223. What point I want to show here? We have a thorium target with a weight about hundreds of milligrams. And first step here is a dissolution in a mixture of nitric acid and HF acid. And after that, we obtained a solution with a wide range of radionuclides, but the concentration of radionuclides is really low. And we have a high concentration of thorium. And the second step, we should remove micro quantities of thorium, and only after that work with the radionuclides by extraction chromatography. Because if there will be no this step, we put the solution on the column, there will be problem with the limited capacity of the column. Another problem that can be appeared during solvent extraction efficient, also problem that we have micro quantities and milli quantities is a so-called co-extraction efficient. Here we try to extract stannum in presence of antimonnia, and if we extract stannum in single mode without antimonnia, we have these distribution ratios. And when we extract a stannum in presence of antimonnia, these distribution ratios go higher by 1 order of magnitude. In case of production, it's important to control the absolute values of distribution ratios. Another big process is isolation of molybdenum-99 because it's a mother radionuclide for technetium-99M. And here it's a really hot example because this is technique based on irradiation of really enriched uranium. I think for now IAEA is banned this process for obtaining of molybdenum because it's a dangerous radionuclide that can be used for nuclear bombs and so on. But what was the idea? There is one problem. Here, when we remove thorium, we can just throw it out with no further usage. But when you work with this target, with this amount of uranium-235 on it, you cannot just throw it out. You should recover and reuse for another target for irradiation. That's why this task is really difficult. You should take molybdenum, and after that, recycle of uranium. And here, so-called synergetic effect can help. What is synergetic effect? We use admixture of two extractants, TBP and HDHP. And here you can see this is distribution ratios of single TBP, no HDHP in this solution, really low distribution ratio. If we use only HDHP, the distribution ratios is higher, but if we use the mixture of these two extractants, the distribution ratios go really, really higher. In comparison with TBP, I think this the grows by hundreds of times. And also a lot of details, but also by use of synergetic mixture, we can more easily scrap molybdenum after extraction. Very important effect. And another example is example of comparison when you make your experiments by imitators of radionuclides and from really solution. Cerium-144 is interesting from fundamental point of view. It used as a neutrino source. And interesting point about cerium, and it can be oxidized towards +4 charge. And by this, it's easily to extract them and don't extract another lanthanides. And just by adding of one equivalent of this oxidizer, we can easily extract cerium. But it works well only on imitators. But if you take a real HLV solution, high-level liquid waste with the lanthanides, no extraction in this condition. And only we take 10 equivalents of oxidizer, we obtain cerium extraction. Why it's so? Because it's a high activity solution, and we can find very much radiolysis products, and most part of the radiolysis products are reductant agent. And they react with the oxidizer, and cerium is still in oxidation state +3. And another really good example of combined work of production of interesting medical radionuclide, terbium-115. This work combines nuclear physics. We should find a good conditions for irradiation of target. We also should design a good target, because during irradiation, of course, all targets heats up, and we should use aluminum for take off the heat. And after we obtained dissolution of target, separation of lanthanides is difficult tasks. And here another problem. During this irradiation, we obtained not pure terbium-155, but the mixture of isotopes. But also this process, we obtained dysprosium. And this dysprosium acts as the mother radionuclides for terbium. So in the first separation step, we removed terbium, we obtained pure dysprosium. Then we wait 1 day for decay of dysprosium. And after that, we isolate pure, from isotopic point of view, terbium. So, brief summary, I don't want to read it. And thank you very much for attention. I'm sorry that I take time from your lunch. Thank you for attention. Any question?
Thank you very much. For my previous research work, I used gas chromatography to detect the concentrations of the compounds I was researching. So do you think it's possible to modify gas chromatography to extract radionuclides?
Well, it's a good question. First of all, I think it's a low range of radionuclides because these radionuclides can be easily go to the gas phase. I think it's works with for iodine. It can be easily sublimate, for example. Another not so usual examples, for example, many radionuclides such as cesium, such as technetium, they can be also relatively easy go to the gaseous phase, but easy here means about 100 of degrees. And in these conditions, I think we can use chromatography, gas-solid chromatography, for isolation of radionuclides.
Actually, I don't have a question, but I have an answer for her question. In nuclear power plants, in case of emergencies and accidents, they use this for radiocesium.
Yeah, thank you very much. It's a very interesting presentation. And I have a couple of questions about the chromatography. So what is the stationary phase you're using?
What, excuse me?
What is the stationary phase that you're using normally? It's a silica?
Stationary phases.
Yeah.
Sometimes is organa is a silica, but with some modification with organic, because contact between silica and organic is low. We should use special technique to put some kind of hydrophobic
It's like
coating.
C18, like
What?
C18 particles, C18.
Yes,
C18.
yes. And sometimes we use just the same polymers.
Okay.
But silica is more stable than polymers in case of radioactive usage of resins.
Okay, and my next question is for the extraction chromatography. You said you're using some kind of resins. So how many times you can reuse those resins?
Well, it depends on many factors. First of all, it depends on type of solutions, because sometimes we can use hydrochloric acid, sometimes nitric acid. Nitric acid is strong oxidizer, and if we work with a strong oxidizer, the lifetime of column is low. Another point is the radioactivity of your solution. If you work with radio traces from environmental samples, it's one case. When you work with isolation of radionuclides from hot targets, it's really another case. So, but just one point here. The manufacturer, the company that sell you this chromatography resins, they can write about it works 10 times. But in real case, it can works 50 times.
Okay.
It's only important. Yes, they degrade, but it's degraded slower than companies tell you.
Okay, thank you.
Hello, thank you very much for the very nice presentation. My name is Matt, and I work in a very, very similar field, but almost the same field, really, because I was struggling with terbium extraction from gadolinium target and multiple resins, the same LN3 resin that you mentioned in your presentation. And I have so many questions that it's easier.
Well, I'm not the author of this work, but I really like this work. I can send you the text of this paper.
Okay.
And the author of this work is Ramiz Aliyev. I think, yes, you can ask all this question to him.
Okay, thank you very much.
Там что-то из интернета. Yes, thank you. So, thank you one more time. Что такое? Да. So that's all for this lecture. Thank you again.
Кого-то еще ждем?
Hi everyone here. Can we start? Once again, our lecturer Rami Saleev and separation of radionuclides from irradiated targets, practical aspects.
Okay. Today we will discuss chemical separation techniques, mostly their application for reprocessing of irradiated targets, but all methods that we will discuss today also applicable for other in other fields, for instance, for reprocessing of rad wastes or other for other purposes. There are several most important chemical separation techniques that are applicable for reprocessing of irradiated targets. First one is liquid extraction. It's very popular and old and reliable technique. And also we often use ion exchange methods, usually in chromatographic mode, and also extraction chromatography and several other methods, especially precipitation or co-precipitation, and sometimes we also use distillation technique for separation of some substances. Co-precipitation is, I think, oldest method that was developed in many years ago, and this method was used by Marie Curie for separation of radium from uranium ore. And but this method also is applicable now for sometimes we use it for separation of trace elements and sometimes also for separation of bulk material of target. As example, you can see separation of barium nitrate when you irradiate barium for production of lanthanum, because barium nitrate is not soluble in concentrated nitric acid, and therefore it is possible to separate bulk barium target material from product of nuclear reaction. And other techniques that we used in our group that was precipitation of silver chloride during production of cadmium. The idea was to separate bulk, to separate bulk material from trace amount of reaction product. And as you well know, silver chloride is not very soluble, and it's easy to separate it from other components. But of course, you will have some co-precipitation of some cadmium with silver chloride. But if you will wash this precipitate, for instance, with nitric acid, it's possible to remove mostly cadmium from silver. And then, of course, you have to purify your cadmium. It is not possible. Typically, it's not possible to make separation of in one step. This is the first step. It's preconcentration. It's separation of bulk material from trace amounts. Also, we used precipitation of europium sulfate when we produced terbium radioisotopes, because, thank you very much, because europium can be reduced to divalent state, and the divalent europium is similar to, for instance, to barium or to other alkali earth elements, and it can form insoluble sulfates. All these three examples were examples of precipitation of bulk material, but sometimes it's possible to co-precipitate reaction product and by this way separate it from target. For instance, we also did co-precipitation of bismuth after irradiation of lead targets by deuterons, and it was possible to co-precipitate bismuth with iron hydroxide, and by this way we separate lead from bulk bismuth. Distillation is also one of popular methods of radiochemical separation, but it's also may be done when we have volatile species with low boiling point. For instance, ruthenium tetroxide, some chlorides or bromides of selenium, arsenicum, and I think germanium also may be removed by distillation from water solutions, because for instance, germanium tetrachloride has boiling point about maybe 80 degrees. It's can be easily separated, and also we can separate by distillation in elemental form some elements. For instance, astatine, but typically it may be done also from as dry distillation from solid phase, but also sometimes it may be done from water solutions. For instance, we separated bromine from water solution by heating in airflow. It was possible to distill elemental bromine in presence of some oxidizer in water solution. Here is example of dry distillation that we performed in our group in Moscow State University. When we separated astatine from bismuth targets, it's a very common method of separation of astatine, and a very simple and cheap and simple method. Here you can see this is a oven when it was heated up to 700 approximately. Target material was heated about 700 degrees, and it was done in airflow. Here we have pump to for air pumping, and here is a drying unit with for instance with liquid nitrogen or something like that, and here on the walls of capillar it was possible to condense astatine by cooling with mixture of liquid nitrogen or with organic solvent, and it was very easy to then to wash out astatine, elemental astatine, from the walls of this Teflon capillar by, for instance, methanol or something like that. It was the idea was to obtain astatine in small volume, and then this volume may be used in a chemical process of astatination of forming of astatine organic compounds. The next very important method is liquid-liquid extraction. It's this method is very common and may be applied as for trace amount of components, and also it may be applied in industrial scale. As you know, liquid-liquid extraction, it's not only laboratory technique, it also applied for reprocessing of spent nuclear fuel, for instance, and hundreds of tons of spent nuclear fuel may be reprocessed by extraction technology. Typically, this is a liquid-liquid extraction is a distribution of compounds. Typically, we use metal complexes between two different phases. One of these phases typically is water phase, for instance, inorganic acids or something like that. And other phase is organic solvent, typically non-polar solvent. In order to predict some extraction processes, you have to know a very common theory that was developed in inorganic chemistry, theory of hard and soft acids and bases. In this theory, you can consider metals like acids and ligands like bases. And in this theory, metals with small ions and with high ion charge typically are considered as hard acids, and soft acids you can consider big ions with large ions and with relatively low charge. And typically for soft acids, it's typical to form compounds with soft bases. For instance, for mercury, it was normal to make compounds with ligands with sulfur, typically, and also for gold and silver. But for rare earth elements, it's more typical to form complexes with oxygen, for instance, carbonates, carboxylates, and other complexes, phosphates and phosphonates, and it was typical for them. Here you can see the location of hard and soft metals in periodic table, and you can see that several soft elements are in these rows. These are typically noble metals, platinum group, and also mercury, cadmium, and silver and gold. Some elements express intermediate behavior. For instance, manganese and cobalt and iron, they may be considered like intermediate, and for this intermediate elements, it is typical to form compounds with intermediate bases, for instance, with bromine, not really hard or soft. More something like more intermediate. And But liquid-liquid extraction is a very useful method, but in order to have a good complete separation of, for instance, two elements, it's not possible to use only liquid-liquid extraction. In any case, you have to purify your elements that is separated from matrix. And for purification, the best way is to use chromatography techniques. And firstly, chromatography was, as method, chromatography was invented by Mikhail Tsvet, Russian botanist, who separated pigments of natural pigments of plants separated by column chromatography with some inert sorbent like calcium carbonate. Chromatography may be done in different modes. It may be done with special devices like high-performance liquid chromatographs, but also it's possible to make chromatography on your laboratory table. It's relatively easy. Here is a simple chromatography column made from pipette, and it is filled with sorbent, and by without any pump, by gravity, it's possible to separate different chemical elements by this very simple and small technique. Usually we use two types of chromatography for separation of elements in radiochemistry. First one and most popular and historically most important is ion exchange chromatography. It's a method when we use organic polymers with functional groups, for instance, SO3H. Here you can see this is a cation exchange. This is a strong cation exchange resin, and this hydrogen may be substituted by other metal, for instance, by rare earth or something else. And it is by this method it's possible to separate positive ions with different charge. For instance, it's very easy to separate, for instance, uranium from thorium, for instance. And by this is an anion exchange chromatography. It's I think it's more applicable, more important, because using these resins, it's possible to separate many elements because of different behavior of elements in different acid media. For instance, you can form complexes in chlorine media or nitric media, and using these differences in chemistry, it's possible to separate elements that form negatively charged ions from others. And here is the periodic table, and here you can see the capacity factors, distribution coefficients. Sorry, it's similar to capacity factor. Distribution coefficient in logarithmic scale. And this is the concentration of hydrochloric acid. This is typical curves for different elements. As you can see, it is possible to retain some monovalent or divalent elements. It's possible to retain is in weak acids. You can see here, and then it's possible to remove, to wash out by a stronger acid. It's a typical way for preconcentration, for instance, different positively charged ions from radioactive wastes or from sometimes from natural environmental samples or others. Similar picture is in hydrobromic acid, but you can find maybe some differences in for several elements. For instance, maybe for iron, this is a little bit different for other elements also. And this is, as for me, this is more important. This is as behavior on anionic exchange. And you can find, for instance, that iron is retained in strong, for instance, iron can be retained in strong hydrochloric acid on the column and maybe separated from other elements, for instance, from first, second, or third groups of periodic table. And also it is possible to separate thorium from uranium, because uranium also will, where is uranium? Oh, here is, because uranium also will retain on column because it forms negatively charged hydrochloric complexes that is, and this is not typical for thorium, for instance, that form in this media form positively charged ions. And here is the same picture for nitric acid. You can, but it's not typical for many elements to form negatively charged nitric complexes. Maybe it is typical mostly for actinides, and usually it is used for actinides. For instance, ion exchange from nitric media is a typical method of preconcentration of plutonium, for instance, from different matrices, such as environmental samples or others. You can see that plutonium-4 can be separated from many other elements because it strongly retains on anion exchanger. And because of differences between elements, you can use these methods for separate them. And also it is possible for separation of rare earth elements, but this is not so easy. You can see here the ionic radii for trivalent elements, and you can see that there is a very small difference between neighbor rare earth elements, but quite a large difference between, for instance, between actinium and rare earth elements, and therefore actinium may be easily separated from rare earth elements in spite of a little bit similar chemistry. And also I want to point out that other trivalent elements, for instance, scandium and yttrium, also have a little bit different chemistry because of difference with difference in atomic radii. But sometimes it is easy to separate mixtures of rare earth elements. For instance, it's not so difficult to separate, for instance, terbium and gadolinium because of the pronounced difference between ionic radii, but it's very difficult to separate praseodymium and neodymium. In fact, it's very difficult problem. And other relatively difficult problem related with nuclear medicine is the separation of ytterbium and lutetium because of similarity of ionic radii and also all equilibrium constants. And here you can see a typical method of separation of rare earth elements. This method, in fact, was developed many years ago in the middle of 20th century. Firstly, it was published, I think, by Gregory Chopin in United States. And these methods also now also actively used for separation of rare earth elements. And this is example from work of Nadezhda Gracheva from Switzerland. This work was intended for separation of terbium from other elements. Typically, this is a sort as a static phase cationic exchanger was used, and as eluent alpha HIBA, alpha hydroxyisobutyric acid was used as eluent that form complexes with rare earth elements, and due to differences in stability constants, it is possible to separate. Sometimes it is possible to separate these elements. The next very useful method is extraction chromatography. This is our favorite method, and we use this method in our practice for many years. The idea is that you have some kind of mixture of liquid-liquid extraction and chromatography technique. In this way, organic phase, a liquid organic phase, is on the surface of inert matrix and may be considered as a stationary phase in chromatography. Here is a solution of some extractant in organic solvent, and mobile phase is water solution, typically some inorganic acids, and by this way you can separate many elements. And now it's very popular in radiochemistry, and we have one company in the United States and one in Europe. They produce similar sorbents. American company is Achrom and the European is Trischem Corporation. They produce a number of sorbent dedicated for special radiochemical tasks. For I think maybe for most of elements important for nuclear fuel cycles, for nuclear medicine, for environmental studies. They have some techniques for radiochemical separation with their own sorbents. And we also use this kind of sorbents in our work. The qualitative parameter of extraction is retention coefficient and or capacity factor. This capacity factor is in fact is location of maximum on elution profile. In fact, this is a number of free column volume that we need to wash out our component from sorbent. The higher is capacity factor, the stronger is retention on sorbent. There are several types of extractants that may be used for extraction chromatography. For instance, liquid anion exchangers, typically amines and ammonium salts. Liquid cation exchangers, for instance, HDHP, it's diethylhexyl phosphoric acid. And also some neutral extractants such as TBP, DJ, CMPO, or others. And also some crown esters, for instance, crown derivatives of crown 18 may be used for separation of some elements, and also ionic liquids, but it's not so typical. The main maybe drawback of method of extraction chromatography and also other chromatographic method is that you have a relatively low capacity of your sorbent system. If you use extraction, sometimes you can separate tens or hundreds, even hundreds of grams in your laboratory. But using extraction chromatography, you can separate only in fact, only milligrams or sometimes tens of milligrams, but really not more in relatively small columns. Here are capacities in milligrams per milliliter for most popular sorbents. But sometimes, as for me, it's better to use lower values that was specified by manufacturers. Typically, it's better to use maybe about 30% of values that suggested by manufacturer. Here you can see formulas, structures of some popular sorbents. This mixture of these two compounds, CMPO and TBP, is the mixture is used in true resin, and true means transuranic. It may be used for separation of transuranic elements. It has a strong retention for both trivalent and tetravalent transuranic elements. Here you can see the equations of chemical reactions for TBP, for instance, with in nitric media, and strongest retention is for tetravalent and hexavalent elements, and weaker for trivalent actinide and lanthanide. And here you can see the dependence of this capacity factor on concentration of nitric or hydrochloric acid. And this kind of pictures are crucial for a development of separation technique. For instance, if you want to separate, for instance, cerium from neodymium, for instance, or americium from thorium, you can see difference in capacity factors for trivalent and tetravalent elements, and you can retain on column both these elements, for instance, in 3 molar nitric acid, relatively high capacity factor for both elements, and then you can wash out americium, for instance, with hydrochloric, with diluted hydrochloric acid. For thorium, retention factor will be relatively high. You can see the big difference here. This picture describes influence of matrix that is extremely important for environmental analysis, not so important maybe for separation of reprocessing of irradiated targets. but for environmental analysis, it's very important because typically when you dissolve soil samples or sediments, you have a lot of iron and aluminium and alkaline earth elements in your solution. And you can see that it is also possible to separate trivalent actinides from in the presence of other elements. For instance, aluminium improves sorption of americium, and calcium and iron 2 don't affect sorption, but iron 3 may also sorb on this sorbent, and therefore may influence to separation of actinides. Here is tevaresin. Tevaresin is liquid anion exchanger, and it is very useful for separation of elements that form negative that can form negatively charged ions in solution. For instance, it may retain tetravalent actinides that form nitric complexes in the presence of nitric acid. And teva means tetravalent. It may be used for separation of tetravalent elements from trivalent. Here you can see the profiles for different elements. For instance, you can see that both plutonium, neptunium, and thorium have high capacity factors, but trivalents such as americium, in fact, don't sorb on the column. It is very easy to separate them. Next important example is DGA resin, diglycolamide. You can see the structure here, and it is useful both for trivalent and tetravalent elements, and in fact it has extremely strong retention of trivalent and tetravalent elements, and also for from nitric and hydrochloric media, and also insensitive to presence of iron. And you can see that the other name is Totga. It's same sorbent. You can see that capacity factor is extremely high. 10 in power 6 approximately for americium, and you can sorb for instance americium and other elements from strong nitric acid and then wash out with diluted nitric or hydrochloric also acid. It is possible, and this is a maybe best way for preconcentration if you need to preconcentrate this element from large volumes. For instance, after dissolution of target, we have typically large volumes, maybe tens of hundreds of milliliters. And if we want to concentrate in small volume, one possibility is to distill this acid, but it's not so good for radioactive solutions, and therefore it's better to maybe preconcentrate using this DGA resin that we typically do it in our group. And here are the capacity factors for different trivalent elements, and you can see that this sorbent may be used for all trivalent elements, and then it may be they may be washed out. In fact, in spite of differences for neighbor lanthanides, this sorbent, in fact, not suitable for separation of lanthanides. It's not so good. For this purpose, we have specially dedicated sorbents. Here you can see profiles for different transition elements, for instance, for bismuth, for copper, for iron. It may be useful for separation, for instance, of bismuth from lead, for instance. It's typical, relatively typical task. DGA is also used for separation of yttrium from strontium. It's a very common task in radiochemistry. Sometimes for separation yttrium-90 from strontium-90, it's one task, and other task is separation of yttrium radioisotopes from irradiated strontium targets in yttrium isotope production. And because of large difference in capacity factors, it's very easy to separate these two elements using this sorbent. You can use, for instance, relatively strong nitric acid, maybe 2-3 molar, and then wash out strontium for loading 2-3 molar, and for washing out strontium maybe dissolved nitric acid. For instance, these relatively low concentrations may be used for chemical separation. Here is example how to separate strontium and yttrium. It's from literature. You can see that it's very, very easy. Other important technique that may be performed on DGA is radiochemical separation of radium and actinium. It's also a typical task both in processing of irradiated target for actinium production, for instance, and other important application is determination of relatively low activities, and actinium may be separated from radium samples for measurements. And you can see that it is really easy to separate d and trivalent elements by this sorbent. It's same, approximately the same like with strontium and yttrium. Maybe one interesting example, but maybe not so typical, is the separation of alkali earth elements. And you can see that it is possible to separate barium from radium, from strontium and calcium using this DGA sorbent. The next example is LN resin that was developed specially for separation of sorry, it's from other slide. Here is a picture of sorbent. The most important is HDHP in LN resin and some other organophosphoric compounds. You can see LN2 and LN3. All these compounds may be used for radiochemical separation of rare earth elements. And here are the profiles for these elements, and you can see that relatively similar behavior of actinides and lanthanides, but in any case, it's possible to separate one from other. And here is the difference between LN1, LN2, and LN3. And it is possible to use any of them, but strongest retention is on LN and weakest on LN3. And if you need not very strong retention, if you want to easily wash out your components from a column, it's better to use LN2 or LN3 than less expensive and more typical LN resin. Here is a distribution of other trivalent elements on LN resins, but typically it is possible to separate them. And then we will discuss several practical examples of radiochemical separation from other from our experience. First one is radiochemical separation of actinium from irradiated from thorium target irradiated by protons. It was really not so easy because the first problem was that the target is relatively massive at about maybe 40 grams or something like that. The target is inside this shell. You can this is surface made from I think graphite or something like that, and inside is thorium. And here is a spot from beam, from proton beam, and it was separated. Then we separated this actinium from thorium in hot cell. And the problem is that during the radiation, you have a very complicated mixture of radioisotopes because of not only common nuclear reactions, but also from fission of thorium. You have a lot of fission products, and you have to separate actinium from lanthanides, also with relatively similar chemical properties. And we used relatively, after months of experiments, we developed a relatively simple method of separation. First was dissolution, of course, of target, and next was liquid extraction in order to remove bulk thorium, but because there is no another way to separate thorium, because in any material is retention for thorium is stronger than retention of actinium. We could not find a system that can be used for concentration of actinium, but not concentrating thorium. And therefore, we used liquid extraction for bulk thorium by HDHP in a relatively strong acid. And then after we separated most thorium, we used DGA column for preconcentration of both trivalent and tetravalent and remaining tetravalent elements. And after we wash out this mixture and separate actinium from lanthanides on true resin. In fact, it's also possible to do it on, of course, on LN resin. It's on your choice. This is a separation on first column. This is at first we load solution. This is loading solution, and several elements don't retain on the column, but in 6 molar nitric acid. This was our initial media after dissolution and liquid extraction. And volume is relatively high, about 100 milliliters. And then we pass this 100 milliliters through the column, and only actinium, cerium, and other fission products, rare earth fission products are retained. They are retained on the column, and then they can be washed out by dissolved nitric acid, and a second purification step was made on true resin. Here is a reference for our article in Solvent Extraction and Ion Exchange. This method was described in details in this paper. The next example is separation of terbium radioisotopes from thorium targets. In this case, we have approximately hundreds of milligrams of europium and trace amounts of thorium and very small amount of gadolinium that also forms during the radiation. And the first step was a separation of europium as precipitate of europium sulfate. For this purpose, we reduced europium by zinc in hydrochloric media. It's a very fast process, and after filtration, it was possible to separate terbium from remained europium and traces of gadolinium by LN resin. It's very easy. Also, you can find details of this work in the article. Next, our task was to separate trivalent lutetium from tetravalent hafnium. It's really very easy, and it may be done by many ways, but this task was rather complicated because we have large, massive targets of hafnium. Typically, we have several grams of hafnium, and therefore it was not too easy. But we did it because hafnium can form complexes with hydrofluoric acid, and we can separate them on LN resin. It was relatively easy. Also, you can find details in this paper. And the next example is separation of zirconium and yttrium. It's a similar task because zirconium is similar to hafnium, and yttrium is similar to potassium, and we developed several methods for separation of these elements. In fact, it is possible to use any sorbent for extraction chromatography for separate these two elements because of great difference in chemistry of trivalent and tetravalent elements. It's possible to use LN or TEVA or UTEVA or TRU, a lot of possibilities for separation. And you have to take into account when you separate rare earth elements that presence of elements in large amounts, for instance, in milligrams, can affect chemical separation, dramatically affect. And if you have more than 2-5 milligrams per gram of sorbent, separation may be difficult. Maybe sometimes you cannot separate similar elements. And one of the most difficult tasks is separation of lutetium from terbium targets. Yesterday we discussed this system, and the typical problem is typically you irradiate in a reactor at least hundreds of milligrams of ytterbium if you want to produce a large amount of lutetium for sufficient for therapy. And it is very complicated task to separate lutetium from ytterbium. One of possibilities is to reduce ytterbium to divalent state, but it's much more difficult than reduce europium. But it's possible to do it electrochemically with assistance of mercury cathode. It's possible to reduce, but it's not so easy to control this process. And of course, it would be better to use a simple column separation. And this method was developed maybe more than 15 years ago by Horvis and company and colleagues. They separated about 300 of milligrams of ytterbium from lutetium from 300 of milligrams of ytterbium, but yield is not in fact rather high, 75%. It's not enough really for industrial applications. They used two columns. This is one of these columns. They, under temperature control, using relatively big columns, they can separate these two elements. But typically it's more easy to separate, for instance, ytterbium from thulium, and we use it for production of these radioisotopes of these elements for our scientific purposes. And you can see that if you have only 2 milligrams, it's very easy to separate. But if you have approximately 20 milligrams, it's not so easy. Same system and same media, but elution profile is completely different. In this case, you have to maybe collect several fractions and then repeat separation. Details are here. And this is one more example that we used for separation of erbium, thulium, and ytterbium. And first step, we separated mixture of thulium isotopes, and then separate erbium from thulium. It was like a generator system from thulium-165. It was possible to separate erbium-165. And next and maybe last example of our work is separation of copper-67 from zinc targets. We irradiated zinc by high energy photons in Moscow State University accelerator, and then separated copper and zinc by specially dedicated sorbent copper resin that was developed by Trischem. And as you can see, it very suitable, very good for separation of copper from zinc. And also it may be used for separation of copper from nickel when you use other methods of production of copper radioisotopes, for instance, by irradiation on cyclotron. Details are here. And the last example is not from our work, it's from literature. It's relatively new research. It was very interesting for me because this was research with astatine. It's very popular and very promising element for nuclear medicine. And in this work, scientific group from United States, they investigated behavior of bismuth, material of target, and astatine on a different sorbent, and they suggested method of radiochemical separation of astatine and bismuth. And the best sorbent for separation was Uteva resin, or maybe some maybe also Ln reason, that it is not so so clear. It's a really interesting result because we have no really reliable information about chemical behavior of astatine. But it is possible to separate these two elements without this dry distillation. It's possible to do it also by methods of wet chemistry. And I think after this lecture you can create your own method. It's really very simple because the main idea is to find such kind of curves. If you have not such kind of curves, you can to build them by your experimental research. It's very easy to measure these coefficients in different media and then find differences between two elements. And if you have a relatively large difference, for instance, 1 order of magnitude or more, it is possible to separate these two elements. Thank you for your attention. I think that's all. And if you have questions, I will try to answer.
Does anyone have questions? Yes.
Thank you very much for the beautiful presentation. Also working with terbium separation, and my most burning question about the setup you used on several slides, you mentioned the appearance of the material in CPS per milliliter. Did you, my question is, did you collect fractions and measure the fractions activity individually, or did you come up with a online system that as the eluate was coming detected the activity of these agents?
Sorry, which system?
Either of the systems where the activity is given on the y-axis as a CPS over milliliter. So is it an online system or is it fractional?
No. We collect fractions and measure them in the same geometry, and it's possible to compare results from different fractions.
I was really hoping for an online system. So okay, thank you. And I will have more questions in private. Thank you very much.
Okay, someone else?
If you have any question, you can ask them during the corruption.
Yeah, right. Oh, yeah. Thank you for your
Welcome.
Sorry, but you are muted.
So we have people in Zoom. Okay. Do you see the presentation?
Yes, we do.
Yeah. Okay. Thank you. Yeah. So let's continue. Yeah. So our lab also work with new biological vectors, especially peptides, for the cancer treatment and diagnostics. Also, another part of our work is related to the new generators. For example, scandium-44, titanium-44 generators. Scandium can be used for the positron emission tomography, and generator systems are very preferable for the medical staff because it is very easily to work with it. And in hospitals, people prefer to work with these generators and not to have special chemists who will synthesize such complicated conjugates. So today I will tell you about the objects that you will work for the next days. Also, I will tell you about how to study them and about our aim. And today will be a short discussion of the TLC method that you will work with this method for the next days. And also during your practical tasks, you will check the complex stability. So let me start with the object. Well, we will study systems that are used as a part of targeted radiopharmaceuticals. This is special systems which consist of biomolecule, chelator that binds radionuclide, and chelator also is linked to the biological vector and radionuclide itself. So the first part is radionuclide. You can use different radionuclides. It depends on the aim of your radiopharmaceutical. So if you want to conduct the diagnostic, you should use some gamma emitter or positron emitters. If you want to conduct therapy, you should use some Auger emitters or beta minus emitters or alpha emitters. For example, here you can see the iodine 125. This is Auger emitter, and Auger electrons have very short range in organisms. So but if you have a very selective system, like selective biomolecule, which binds to the receptor on the tumor cell, and there are some systems that can go inside the tumor cell and go to the nuclei of the cell, you can use these Auger emitters, and it's very very good because due to the short range, you damage particularly this tumor cell, and you don't damage the healthy cells around this tumor cell. So it's quite effective for the treatment of the metastasis and small tumors. But such biomolecules are very rare, and usually for the treatment you use only systems that binds only to the receptors on the surface of the tumor cell. And for this purpose, you can use beta minus emitters or alpha emitters. Here are examples of the beta minus emitters, like iodine 131, yttrium 90, and during your work you will work with the yttrium 90, quite popular radionuclide in nuclear medicine. And also another famous radionuclide is lutetium 177. All of them just broadly used in the nuclear medicine. Beta minus emitters are used for the treatment of the rather huge tumors, because beta minus particles have rather long range, and alpha particles have much more shorter range, and alpha therapy is used for the treatment of the small tumors and small metastasis, cancer, and etc. And actinium 225 is, I guess, the most popular alpha emitter which is used in nuclear medicine. Then we move to another part of this conjugates, targeted radiopharmaceuticals, and this part is biomolecule itself. Biomolecule delivers the whole conjugate to the tumor cell and binds to the receptors on the surface of the tumor cell. There are some biomolecules that are broadly used in nuclear medicine. I guess the most popular one is a PSMA molecule, which is used for the treatment of the prostate cancer. And last year, FDA, Food and Drug Administration of USA, approved the drug which is called Pluvicto. It is based on the PSMA molecule and chelator that binds lutetium 177. And lutetium is quite popular radionuclide in nuclear medicine. So with the help of this drug, you can treat the prostate cancer, and to visualize the then to conduct the diagnostic of your treatment, you can use the same biomolecule, but you should use some gamma emitter or positron emitter, like gallium-68. And here you can see the positron emission tomography scans. So on the first picture, you can see a man with a lot of metastasis in the organism. And on the second picture, you can see the patient after the treatment with Pluvicto. And you can see that results are quite successful. And the third part, another biomolecule which is also quite popular in nuclear medicine is octreotide, which is used for the treatment of the neuroendocrine tumors. And here again, you can see the lutetium complex with the ligand daughter, like in previous one. And this drug was also approved by the FDA in 2018. And it is called Lutathera. And again, you can see the scans of the patient, but this tumor is quite small, so you can see on the scan this small glowing dot. So you can see the accumulation of the Lutathera there. But PSMA molecule and octreotide molecule are short peptides. They're short peptides, but you also can use larger biomolecules such as monoclonal antibodies. And here also there are two popular substances, drugs. One is based on the yttrium-90, which is called Zevalin, and it is based on the ibritumumab antibody. And another one is based on the iodine-131, which is called Bexar. But antibodies are very huge molecules. And the problem is that if you work with antibodies, they are very sensitive, and mainly they are very heat sensitive molecules. So here, if people create some drugs based on the antibodies, usually they used another chelator to bind the radionuclide. So here you can see the DTPA chelator, and you can see that it is a cyclic chelator, and previously you can see that DOTA is macrocyclic chelator. It's quite important, and I will tell why further. Yeah, so another part of this targeted radiopharmaceuticals, we discussed radionuclide, we discussed biomolecule, and now we discuss this important part which link biomolecule and radionuclide. So, and this is chelator. Mainly in nuclear medicine, scientists use only two chelators. It is DOTA or DTPA. And they have, both of them have disadvantages and advantages. DOTA is macrocyclic ligand, and it binds radionuclides to very stable complexes. So conjugates with DOTA usually are very stable inside the organism, but the disadvantage of the DOTA is that the kinetic of the binding is very low and very slow. So you need to heat the substance to form a stable complex. And this is the reason why with short peptides we can use DOTA, because short peptides are not so heat sensitive, and you can heat your mixture up to 60 or 90 degrees. But you can't use DOTA with antibodies because they're heat sensitive. And with antibodies, usually the DTPA ligand is used because it is a cyclic ligand. It forms complexes very fast. But the disadvantage of the DTPA is that usually the complexes with DTPA are not so stable inside the organism. Yeah, as I mentioned, you will work with yttrium-90, and to obtain yttrium-90, you will use the generator system. So you will obtain yttrium-90 from the strontium-90. Generator systems are quite popular in nuclear medicine because they're easy to use. So in your work, strontium-90 will be the mother radionuclide. It has a longer half-life, and from time to time you can milk yttrium-90 as it is shown on this picture. And these systems are used in hospitals also. So for example, one day you milk yttrium-90, then some days passed and you again can milk the yttrium-90 from the generator. Yeah, so this is this generator system. You can see that half-life of the yttrium not so big. And it is beta minus emitters with a rather high energy, and it doesn't have gamma radiation, and this is why during your work you will, to count the radioactivity of your samples, you will use liquid scintillation counting. Generators on the strontium yttrium generators are based on the strontium resin. So you put the solution of the strontium yttrium on strontium resin, then you wash and milk yttrium, and then you can remove the strontium from the system. But I guess we will do it by ourselves because it's rather high radioactive. We will discuss it. Yeah, so yttrium-19 is quite popular radionuclide in nuclear medicine, and it is used for leukemia and lymphoma treatment, and you will deal with it. Our objects will be these two chelators that I mentioned. DOTA, macrocyclic ligand with slow kinetics, but it forms stable complexes. DTPA kinetics, the DTPA ligand with the fast kinetics. And EDTA, this is also a cyclic ligand. And this object you will also have during your work. The discovery of the new ligand is a very important task, because this system is linking two very important part of the radiopharmaceutical. And if the ligand doesn't form stable complexes, the whole conjugate doesn't work. And small changes in the ligand structure change the stability of the conjugate, change the labeling efficiency of the conjugate, and the biodistribution in the organism dramatically. So on this slide, you can see the main part of the ligands that are discovered nowadays. You can see macrocyclic ligands like PEPA, HEHA, PITA, MACROPA, and also acyclic ligands with picolinate arms. So our aim will be to study chelators like people in this field do. When they get new ligand, they conduct such study, and you will do also this work. Yes, and as I mentioned, the research of the chelators is the separate and important task, but how to do it? First of all, when you have a new ligand, you characterize it, for example, by nuclear magnetic resonance and potentiometric titration. But then you start to research the study complex behavior. So you test the labeling efficiency. It's quite important characteristic because if you have this characteristic is related to how much ligand do you need to fully bind your radionuclide. And if the concentration is not big, it's very good, because it means that this ligand is quite selective. On the next step, you conduct the determination of the complex stability. First of all, you determine the thermodynamic stability constants of the complex. And for this purpose, you can use potentiometric titration and extraction. And then you conduct the kinetic stability. You determine kinetic stability of the complex in different media. For example, in acidic media, you can understand what mechanism is for the complexation and dissociation. And it's quite important, because if you for example, discover that your complex is not stable in blood serum and in the organism, the experiment in acidic media help you to understand the mechanism of this dissociation. How does it occur? And what you can change in the ligand structure to make it better. And then you can do the kinetic stability, determine kinetic stability in isotonic solution, in blood serum. And for this purpose, you can use thin layer chromatography and also precipitation of the peptides with the counting on the liquid scintillation counting. And you will do these both methods. And finally, if the complex is stable in vitro, you can move to the determination of the stability in vivo. So to conduct biodistribution study inside normal mice and mice with tumors. Yeah, so now we switch to the, as you can see, thin layer chromatography is used in these steps. In labeling efficiency, first of all, you can use thin layer chromatography. And also for studying stability, you can also use thin layer chromatography. And now we will talk about this method. This method is used to separate a mixture of the substances. And this is quite popular method because it is quite universal and express, and there are a lot of commercially available sorbents and eluents nowadays. It is quite selective, and you can conduct qualitative and quantitative analysis of your mixture. And chromatography is used in broad areas of our lives, starting from pharmaceutics, not only radiopharmaceuticals, but also for vaccine purification, which is quite important now, for diagnostic, for quality control of the food and any kind of products, for water purification, and in criminalists. Yeah, so in chromatography, you have stationary phase and mobile phase. Mobile phase moves along the stationary phase. Stationary phase can be called like sorbent, and mobile phase is called eluent. In thin layer chromatography, TLC, we have solid stationary phase and liquid eluent. So you have a TLC plate, which is covered with some sorbent, and you place your sample on the starting line, and then you place the plate inside the flask with the eluent, and then the mixture of your substance somehow distributes on the surface of the plate, and that's how you can distinguish them. And you will do the same. So here is flasks that you will have. Here we put the eluent, and then you put your sample on the starting line, and then you place the plate inside the flask, and close the flask, and then eluent runs along the plate. And you should be careful not to drown your starting line with your sample, because otherwise you will not conduct your separation. This movement of the eluent along the plate occurs due to the capillary forces. This is quite similar to how trees obtain minerals from the groundwater. So from the ground up to the leaves due to the capillary forces. And it's very important that components of your mixture that you place on the starting line moves along the plate with a different speed. And this is why you can distinguish them. Separation conducts this way. So your sample is diluted in eluent, and then it is somehow distributes with the surface of the TLC plate. And this equilibrium conducts in each theoretical plate, and the whole plate, TLC plate, consists of a lot of theoretical plates. Due to the different equilibrium for each substance, you can the movement, each substance move with a different speed, and you can distinguish your substance on a plate. But why do the components move at the different speed? The short answer is that the substance have different chemical nature, and mainly the polarity of your substance plays the crucial role. So here we have one substance that runs very fast. For example, it's more polar, and another one doesn't run because it is much more less polar. To change the distribution of your spots on the plate, you should change the eluent or stationary phase. But usually it's much easier to change eluent somehow and obtain better resolution of your substances. And here's another example. We mixed, we have a funny example. These are glowing sticks, and we mixed, you can take if you want after this seminar. We mixed some colors of these glowing sticks and put it on the TLC place and conducted a thin layer chromatography on the different systems. And here you can see, I will distribute it and you can give to others. You can see the different distribution of these spots on the surface. And here is also the photo. You can see that in a system with ethyl acetate, both dots run with the front. In hexane, it stays on the starting line. And if you somehow mix these two elements, you can obtain some resolution of these spots. But and it is what you will do tomorrow. You will try to obtain appropriate separation system for your complexes, where free yttrium will be separated from the yttrium complex. Yeah, so in thin layer chromatography, we have some commercially available stationary phases. And again, I will distribute some of them. You can use just paper for the TLC analysis. Another, I guess the most popular is silica gel on aluminum, and it is also here. And I will also give you this, and you can distribute. This is paper. This is silica gel on aluminum, and on the glass baking. And this one is ITLC plate. ITLC plate is very quite popular in nuclear medicine because it allows to move eluent very fast. And it is used for the analysis of the radionuclides with a short half-life. So if you have a radionuclide with a short half-life, the analysis should be conducted very fast. But ITLC is not appropriate in a lot of systems because it doesn't give very good resolution. So usually researchers use silica gel on aluminum. And eluents can be any eluents, but usually if you analyze polar substance, usually you have more polar eluents. And for example, if you have organic substances which are not polar, usually you have non-polar eluent. But you should be very careful. If you mix some liquids for the eluent, they should be soluble in each other. So, for example, you can use water and methanol, and you can't use very polar and non-polar eluents together. What influences the separation in TLC? Well, the main part is the choice of stationary and mobile phase. And you can change one of the commercially available TLC plate. They also have different parameters like size of the sorbent particles, impurities. Impurities are very important because for the analysis of the radioactive complexes, we should have very clean surface, because the concentration of the radioactive complex is very low. Also, the plate preparation plays an important role. So usually the standard protocol of the TLC tell us to saturate the plate before the analysis. And you will also do this. So first of all, you will saturate the plates and then dry it and then use it for the analysis. Sample application also plays an important role. So we will ask you to put a small dot on the starting line as you can do, because if the spot will be very big, you will not have good resolution of your spots. Yes, and dilution also plays an important role, but usually in most cases we use an ordinary elution where we put the plates inside the flask with the eluent. But how can we identify our substances on the surface of the TLC plate? Well, some substances have like natural color, like this, like in this example. You can see it by your eyes, the distribution of the plate, of the spots on the plate. But sometimes substances doesn't have any color. In this case, you can use intrinsic fluorescence or use the fluorescent layers that are also commercially available. So in this case, you put your TLC plate to the ultraviolet light and see the distribution of the spots. Also, you can do some chemical reactions with the which gives colored products, and again you can see it by your eyes on the surface. And radioactive methods which we will use if you have radioactive complexes which are distributed in a plate. You can use, for example, digital radiography, where you can see the distribution of the radioactivity on the surface of the plate. The main characteristic in thin layer chromatography is retention factor. So you have on the picture, you can see three substances. And for each substance, you can count the retention factor. For example, for substance A, it is distance from the starting line to the middle of the spot, divided to the whole distance of the eluent from the start to the front. And in particular system, in particular stationary phase, in particular eluent, you have the same retention factor. So if you have standard samples, you know the retention factor for each substance, and then you can analyze the solution with the composition that you don't know, and you see the distribution of the spots, you count the retention factor, and you can say what substances do you have in your system. If we work with the radioactive complexes, you will use digital radiography to obtain some pictures which are similar to this one, but maybe not so complicated because we analyzed their quite complex system here. So you can see the how it is conducted. You place your TLC plate on a special radioactive sensitive plate, and some tracks appears in this sensitive plate, and then you scan this plate and see the tracks of the radioactivity on this plate. So for example, here you see the spots of the colloids on the starting line. This was a system of bismuth complexes and conjugates. On the front, you can see free radionuclide complex and the conjugate with the octreotide. Yeah, and then I will tell you what are you going to do. For tomorrow, you have 2 tasks. First is the preparation of the yttrium labeled complex with daughter ligand. I will remind you that you will analyze these 2 chelators, daughter macrocyclic ligand and acyclic ligand DTPA. So back to the task. Yeah, and for the system of the yttrium labeled complex with daughter, you will select an appropriate system for the analysis. You will have silica gel, yes, silica gel, and 2 different eluents, and you will see how the substances distribute on these plates, and you will choose the appropriate system for the further analysis, which you will do on Friday. And another task is related to study serum stability of the yttrium labeled complexes with acyclic ligands, DTPA and EDTA. For this, you will place your labeled complex to the serum, to the blood serum, and then you mix it. And from different periods of time, you will take an aliquot from this solution, and then you precipitate the serum peptides with the ethanol. Then you conduct the centrifugation to precipitate the peptides. And if the complex dissociates, free yttrium will be released, and the free yttrium will be bound to the serum peptides, and they will be separated during centrifugation. And in solution, only complex stays, and you will take this solution after peptide precipitation to count the radioactivity in liquid scintillation counting. And on Friday, you will understand what system or what TLC system you should use for the analysis, and you will conduct the, you will determine the labeling kinetics determination of the yttrium labeled complexes with DOTA. So you will heat the sample, and from different periods of time, you will take an aliquot from this solution and check how many complex has already formed at this time. And for each sample, you will count the radiochemical yield, which will show the labeling efficiency of the DOTA ligand. And there are some safety rules that I want to discuss with you. Well, we have a special dosimetry staff. It will also work with us because we will work with yttrium 90. It is radioactive solution, but the levels of the radioactivity will be appropriate for you. So you should not worry, but you should work carefully with the radioactive solutions. And when you come to the lab, you should wear gloves, and I will ask you do not throw the gloves to the bin. When you finish your work, the dosimetry staff will come, check whether your gloves dirty or not. If they are dirty, they will be moved to the radioactive waste, and if not, we will just throw it in the bin. And you also should wear a lab coat, and I will ask you, you will work in a lab where also other students work, and I will ask you to not touch any things that are not related to your work, and just walk carefully with the radioactive solutions. Also, you will have special vial on the table for the radioactive waste, one for the plastic, for example, for the tips or pipettes that you will have, they will be marked, and another vial for the radioactive liquids. If I don't forget anything, it's all I wanted to say. Yep. Yeah, so that's the plan for the tomorrow. Yeah, thank you. If any questions, I can answer. Okay. So if no question, we finished for tomorrow for today, and we will meet tomorrow at 10 o'clock, I guess. At 10 o'clock, we will start our practice, and we will tell you what to do tomorrow.